Hello, everyone. Hello, chat. Hello, friends and furs, gays and gamers. How's everyone doing today? We all holding in there? Let's see here. It's time for the games to begin. Oh yeah, let me see. I do this here, yeah? And then I turn off the controller capture. Perfect. Okay. So, last time, the first meeting. Hey, Phobos. So the first time that we met. Hold on. Cut that out. Let me get this going here. Is this what I want to listen to? Sure. So, the last time we met, last Sunday, I did a review of like pre-calculus. We didn't necessarily cover like everything, but we covered like functions, plotting points, rational functions. You know, to a certain extent, we covered a little bit like about like what does it kind of like what does it feel like it means for us to kind of like approach certain values, or for things to be continuous, or for things to, you know, be smooth and all that sort of stuff.
So cool.
Thank you. Sounds like he needs a glass of water. But we didn't exactly quite cover everything, but we're gonna go through like the preface questions from the book today, after we kind of get through some of the trig stuff that I want to cover today. And then we'll go from there. And so if, you know, for whatever reason there isn't something that we covered that we should know, then hopefully the preface will have us covered. Can you be my personal tutor? None. But you're always welcome to ask me questions, and I can answer them if I'm available. But so let's jump straight in. And so trig functions and ratios. So what is the deal with trig functions? And so the whole idea with trig functions is that they discovered back in like the Greek and Roman times or whatever, or just probably the Greek times. The Greeks are the ones who did all that stuff for the most part. Here, I'll use the lines. Why? I will bribe you? I don't need to be bribed. Like, I don't have to be your personal tutor. You can just ask me questions and I'll answer them. But if I'm your personal tutor, then that means I can't help anyone else. And this knowledge is for everyone. And so, what they figured out back in the times of like the ancient Greeks or whatever, is that if you have a triangle, then if you take the ratios of some of the sides of the triangles, then you always get basically like the same value, regardless of whether you like scale that triangle up or down. And so, you know, it's to say that if we say that this is some angle here, and so if I call this angle alpha, and then this angle can be beta, then if this is 90 degrees, I almost drew an F. If this is 90 degrees, then what they figured out is that I don't really have a question just yet. I'm not stuck on anything. Just my tiny brain understands most of the time what I read. Right. Well, follow along. And so that's why we're here today, right? To learn some things. And so basically what they figured out is that if you take like, say the ratio of this side, and so I guess I'll call this side A and this side B, and then I'll call the hypotenuse C, then if you scale this triangle up or down so that the angles stay the same, then A divided by C is always equal to like the same number. And so like I'll just call it, I don't know, X for the sake of this. And if we were to instead do like B divided by C, then that will also always be equal to the same number, as long as the angles are the same. And so like you can scale the triangle up or down, you can make it all bigger or smaller, you know, kind of whatever you want to do. And so if it's really small or if it's bigger, you know, it doesn't really, as long as the angles stay the same in the triangle, you always get the same number when you take the ratio of their sides. And so maybe for B divided by C, this could be like Y, and if we do A divided by B, this could be C. Or this could be Z. And so the whole idea here is law of sines moment. Yeah, exactly. It's in there somewhere. But the whole kind of idea here is they kind of figured out, okay, well, what if we do have like the angles change a little bit? Like, what if we said like this angle alpha, like if I get beta out of here, if we just kind of think of everything in terms of like angle alpha, if angle alpha increases or decreases, then how does that affect like the side lengths? And moreover, how does that affect like the ratio of these side lengths? Because if they always get the same number when the angle's the same, well then what happens if the angle changes? And that's where these trig functions come from. And so effectively it's basically like saying, you know, if you take like the sine, cosine, or tangent of this function, then for that kind of scale of triangle, you're finding out like what that ratio of A to C or B to C or A to B is. And so if you've taken trigonometry, you might have heard it before, but there's kind of three trig functions that we usually start with. So there's sine, cosine, and theta. Or I'm sorry, sine, cosine, and tangent. Getting my words all mixed up today. And sine, cosine, and tangent are all functions. And so the reason why I bring that up is that they're functions is because, like, you know, functions like take in a certain type of number. And so like whenever you take the sine, cosine, or tangent of anything, you're taking the sine, cosine, or tangent of an angle. And so angle is usually represented with theta. And so it's finally at this point in trigonometry where it's like they start to realize, oh crap, we might be running out of good letters to use in the alphabet for all of the algebra and things that we want to describe. And so we start using letters from the Greek alphabet, and so that's fun. And so usually Greek letters often end up like notating like angles and things like that, but that's not necessarily always the case. It kind of just depends on what you're doing. And so sometimes Greek letters can be like, anything. Like at various different constants. Constants come up all over the place in math and physics. But yeah, and so sine, cosine, and tangent. And so these are respectively equal to like the opposite over the hypotenuse, the adjacent over the hypotenuse, and the opposite over the adjacent. So here, let me move this a little bit. And so what that looks like in terms of our triangle, and so if I just copy and paste this here, I'm just going to select, there we go. So if I just copy and paste this down here, then instead of alpha and C and B and A and all that stuff, if we say that this angle right here is our angle theta, then if we're taking the sine of theta, then what we're interested in is what side is opposite from this angle. And so the opposite from this angle is this side over here. And so this side is what we call our opposite. And so I will label that as so. And then the side adjacent to this theta, well, you could look at it like either this side down here is adjacent or this side up here is adjacent. But then what would we call our hypotenuse? Well, the hypotenuse for a right triangle, hopefully you'll remember from geometry, is always the side that's directly opposite the right angle. And so the side across from the right angle is always the hypotenuse. So this side is the one that we label as the hypotenuse. And then this one down here is the one that we'll label as the adjacent. And so for a given triangle, you can scale it up or down as long as the angles stay the same. Then the idea is that there's these functions, sine, cosine, and tangent, that essentially tell you like what the ratio of the side lengths are in some description. And so there are kind of like other important ramifications of this. Like, we know that if this kind of all ties to like a right triangle, well, let's consider like a right triangle where we fix like one of the values to be something specific. And so like what happens, for instance, if I were to fix this hypotenuse to have like a value of 1, well then, we don't necessarily know what this opposite side is, but because it's vertical, because it goes up and down, let's call it y. And then the adjacent, we don't know what it is either, but for the sake of it, since it's horizontal, let's call it x. And so then if we were to start writing out what the sine, cosine, and tangent were of this triangle, well then I would get that the sine of theta is equal to the opposite over the hypotenuse, which would be y over 1. And then the cosine of theta, which is, our base down here, or it's going to be our adjacent over our hypotenuse, is going to be x over 1. And so, you can ignore for a moment that, like, actually, now that I think about it, like, I could have just labeled these, like, A and B, for instance. But one of the things that you can, like, think about and realize is that, these are just, like, the bases of our right triangle. And so if we had a hypotenuse of 1, then cosine is just equal to one of the legs of our right triangle, and sine is just equal to the other leg of our right triangle. Well, what do we know about the legs of a right triangle? Well, we know that, I labeled these both B. Here, I'll label this one A. we know that like for this specific triangle right here, then we can say pretty confidently that a squared plus b squared is equal to what would end up being 1 squared. And so if over here, if I wrote this, that sine would have been b over 1, and cosine would have been a over 1, well, that just means that sine and cosine are both equal to a and b, respectively. And so I could make a substitution, that this would be cosine of theta all squared plus sine of theta all squared is equal to 1, because 1 squared is 1. And so there's algebra and there's different things that you can do with trig functions. And we do have a slightly different notation for these. And so oftentimes how you will see this formula written will be, they'll usually put sine first, just because, like, you know, you have sine and cosine. And so sine is usually the one that's, I guess, kind of like given priority in terms of like writing one first and the other second. But so you'll usually see it written like this, where it's sine squared of theta plus cosine squared of theta is equal to 1. And these mean the exact same thing. And so this and this one here and this one here are equivalent. They're equal. And so it doesn't mean anything different. And so sine squared of theta just means that you have sine of theta all squared. And so why do we care? Why is this relevant? Well, to kind of learn why that's relevant, we do kind of have to, you know, talk about a little bit. One of the things that we didn't cover with the pre-calc stream last time, and that's just like graphs and equations of like circles and things like that, for instance. Here, let me move this. And so like graphs of equations of circles. So how do we graph like a circle? Well, one of the things that we can kind of start with and think about for like the graph of a circle, if this is our x-axis, this is our y-axis, then like what do we know about a circle? Well, we know that like a circle is basically all of the points that are the same distance away from the radius. And so like whether I put a point here, or I put a point here, or like I put a point down here, then the distance from this point to the center of the circle will always be the radius and will always be the same. And so whether we go this way, or whether we go this way, or whether we go this way, the circle equation is x squared plus y squared equals r squared. Yeah, that's correct. But why? And so, you know, one of the things that you might notice is that basically like we're kind of asking ourselves, okay, well, we want like basically the function where the point from the center of the circle to the edge of the circle is always the same. And so it's like the distance.
Bro, I've heard of alpha males, I've heard of beta males, I've heard of sigma males, but what the fuck is a theta male? I gotta get me one of them. Can a brother tell me where I can find myself a theta male?
I don't know. Maybe it has something to do with the position in the alphabet. I don't know where theta lies in the Greek alphabet. But so, like, if we were just to say, you know, for instance, let's say for a moment that the radius of this circle was 4. And so the distance from the center to the edge is 4. Then if I wanted to find, like, the distance from, say, like, the center to this point, then I know that the center is at 0, 0. And I know that this point over here would be at 4, 0. And so we can find the distance between those 2 points pretty easily. If you remember our distance formula, then we've got that the distance is equal to the square root of x2 minus x1 all squared plus y2 minus y1 all squared. You can't distract me with gnomes. I'm in the zone. the gnome free zone. What was I doing? Shut up. And so what we can say is that, like, you know, we can find this distance, and it'll be equal to 4 just because that's our radius. So this is kind of like the obvious example. But basically, like, it's like our change in x squared plus our change in y squared, and then you take the square root of that on both sides gets us our distance. But what if we, like, rearrange this a little bit? So, like, what if we were to square both sides? And so now we would get, like, our distance squared is equal to x squared, or x2 minus x1 all squared, plus y2 minus y1 all squared. And then we could also take advantage of the fact that one of our points is always at 0. It's always at the origin, since it's going to be like the center of the circle. At least this will always be true for the equations of circles that are centered at the origin. And so then what we get here is that if one of our points is always at 0, 0, then let's say that, like, x1 and y1 are just both 0. And so, well, what will x2 and y2 be then? Well, x2 and y2 will be whatever point on the circle we want. And so it could be like our 4, 0. And so, like, in that instance, if we were to try this out, then we would get that d squared is equal to, in this case, it'll be 4 squared, and then plus 0 squared, if we were to plug this point in up here. And so what's d? Well, if this is d squared is equal to 4 squared, then that means d has to be 4. What if we try, like, a different point? And so, you know, so I know that one of the points on this circle, like, let's say it was given to you, that we could know for sure that the one of the points on the circle is, like, 2 square roots of 2, like, comma, 2 square roots of 2. I think that's correct. There's 2 square roots of, yeah, a square roots of 2. Yeah, so this should work. And so what if we wanted to figure out, like, what the distance is for this point? Well, that would be d squared is equal to 2 times the square root of 2 all squared, plus 2 times the square root of 2 all squared. And the 2 square roots of 2 squared is going to be 4 times 2 is 8. And then 2 square roots of 2 squared again is going to be 8. And so then we have d squared is equal to 16. And so once again, that gives us that d is equal to 4. And so the distance between them, like, you know, the distance from the origin to whatever point we're on the circle, it's just 4. And, you know, that's obvious because 4 is the radius. And so there's, like, a totally other way that we can kind of view this equation here that we've been working with, where, you know, if this is, like, just going to end up being our x value. So, like, if this is our x value and this is our y value, and this just ends up being our radius, well, then that gives us an equation. We can say that the equation of a circle, like Uncle Talk said earlier, is going to be x squared plus y squared is equal to r squared. Once again, this is only true for circles that are, you know, centered at the origin, but we can apply everything that we've learned so far, kind of about transformations, to this as well. And so if I were to go onto Desmos here, and so if I typed in x squared plus y squared equals r squared, and then I can add a slider for r, then we can see when r is 1, then we get a circle with a radius of 1. If we increase r up to 2, then we get a circle with a radius of 2. And so on. It's like magic. But then we can also kind of do what we did last time, where we can, like, add or subtract values directly from the x value or the y value. And so if I make this like x minus a, or here, I'll use what we used last time, which is like h and k. You usually see h and k with transformations. Where now you can see, like, if I increase h, the circle moves left or to the right and to the left. So specifically increasing h makes it move to the right, and then decreasing h makes it move to the left. Increasing k makes it go up, decreasing k makes it go down. And in theory, we could talk about like multiplying x or multiplying y by like given values to kind of represent like vertical stretch or horizontal stretch and that sort of stuff. But there are other ways to go about that for like the equation of an ellipse. And you know, ellipses basically are just like what you get when like this r value, you kind of like split it between like x and y. You know, I can actually show you that here. The equation of an ellipse it's usually given as like the same thing, except this would be like over a squared, and then this one would be over b squared, and they would all be equal to 1. And so you could imagine, for instance, that if a squared and b squared were both the same number, then you could just multiply both sides by that number squared, and you would get your circle equation, and so it would look like a circle. However, if a and b weren't the same number, then you get an ellipse. And so we can stretch this ellipse out kind of whichever way we want, and kind of how wide or how short it is in one direction as compared to the other is dependent on these values of a and b. And so you could even go so far as to say that the circle, the equation for the circle, is just like a special case of the equation for a ellipse, where a and b are the same. And there are other things too, like hyperbolas, where if instead of adding them, we're subtracting them, we get this funny shape that's like a hyperbola that has 2 diagonal asymptotes. But I don't think we really need to get into hyperbolas today. You know, they will be relevant, like eventually later on, but more so whenever you kind of get into the calculus of multiple variables and stuff like that. And so single variable calculus, you know, they don't end up being very relevant. If you'll give me 2 seconds, chat, I need to figure out what my cat wants. I will be right back. Okay, I'm back. So that's pretty neat. And so one thing that we can kind of bring up here as well, and so what if we kind of like take this idea here, where we have like a right triangle and the hypotenuse is a specific value, and we take like the sine and cosine of that right triangle, like at this angle down here, and we kind of like see what happens. But we kind of do that like on top of the equation of the circle. And so something really interesting actually happens. And so if I just grab these things here, can I select both? No. and then order that, send it to the back. Did that even work? Bring, okay. I guess it worked, I just can't tell. So here, let me make this bigger. So let's say we've got this circle here. And let's say that the radius of this circle is 1. And so we have a radius coming out this way, and the radius of this circle has a length of 1. Then, for any point that this radius ends on, and so for instance it could be, you know, this point right out here, like this, then we can actually take this point in this radius and essentially use it to like construct a right triangle. And so if we let it drop down from this point here, and then we come over from this point, then we have a right triangle. And so then we can, you know, measure one of the angles on this right triangle. And so we could, for instance, say, okay, well, this angle right here, we'll call this angle theta. And so then what do we get? Well, this is in a coordinate plane. And so this can be the x-axis, this can be the y-axis. And so this point here, it's some point that we don't know necessarily right now. But we can say it's at like x1, comma y1. And so that's all so far so good. But, you know, what is x1 and y1? Well, x1 is the horizontal distance that we've moved over this way from the origin, and y1 is the vertical distance that we've moved up this way from the origin. Yeah, it's technically from like, you could think of it more so from like here to here. But that will be like the same vertical distance as this side of the right triangle over here, because they're both the same height. And so what we can do is we can say, okay, well, the cosine of theta, or I'll start with the sine of theta of this triangle over there, is going to be the opposite, which I'll call y1, or what we called y1, and it's going to be over our hypotenuse, which is 1. I'll draw this one with the orange too. And then same thing we can do for cosine. And so then we can say that the cosine of theta is equal to, it's going to be the opposite, which is x1. And so the opposite, which is x1, and then it's going to be over the hypotenuse, which is 1. And so another thing that we've said is that now effectively that the sine of this angle is going to be equal to whatever y1 is, whatever this coordinate is. And the cosine of this angle is equal to whatever this coordinate is. And so once again, you know, I feel like it's important to point out that this is technically only true for like a unit circle. And so the moment this denominator down here isn't 1, or rather that this radius isn't 1, because this denominator and this radius are the same number, then like sine theta and cosine theta aren't directly equal to x1 and y1. You know, it will be sine theta, and then you have to multiply both sides by that radius to get exactly what y1 is. But you know, this is great for the unit circle, because the unit circle is effectively, you know, how you can figure out kind of like what specific values of trig functions are easily. And then you can like scale them up or down, you know, in some circumstances where you actually need them to represent, you know, different things that aren't part of the unit circle.
Wow, this math is really interesting. What do you think about this sine theta and cosine theta? Do you think it should equal 1? Or do you think they could go bigger?
Oh, don't even get me started on sin theta and cosine theta. They're like two peas in a pod, always teaming up to make sure the Pythagorean identity stays true at 1. But imagine if they could exceed 1. That would be like discovering a lobster-shaped banana milk galaxy. How delightfully chaotic. Yep.
The Pythagorean identity. There it is. That's what we were talking about earlier. And so I actually didn't call this the Pythagorean identity, but that is what this is. And it's called the Pythagorean identity because it comes from, you know, the Pythagorean theorem. Imagine if they could exceed 1. And so one thing that you can think about here, though, is, okay, well, so if what we figured out is that the x-coordinate here is going to end up being cosine of theta, and the y-coordinate is going to end up being sine of theta, well then how do cosine and sine relate to each other? And if these are functions, like what do they look like when they're graphed? And so one thing that you can kind of think about is like, all right, well if theta is 0, then that means that like we would have a point down here. But as theta increases, and so like as it sweeps up and rotates, like as this line sweeps up and rotates around the outside of the circle, well, our x-coordinate has to get smaller and our y-coordinate has to get bigger. Because you can kind of see from this point here to this point here, well, we've come in on the x-axis, but we've gone up on the y-axis. And then by the time we get to this point over here, well, then you can really see, okay, well, we've come all the way in on the x-axis, but we've gone all the way up on the y-axis. And then as we kind of continue around, our x value starts to become negative and our y value goes down until we get to this point. And then our x value goes back towards 0 and our y value becomes negative until we get to here. And then it all kind of changes again. And so you can kind of think of it as like, you know, as cosine, like as the theta increases, you have like cycles of cosine increasing and decreasing and sine increasing and decreasing. And if sine is increasing, then cosine is decreasing. Or if cosine is increasing, then sine is decreasing. And it kind of has this like, you know, like you can imagine kind of like if we were just looking at the sine value, so sine of theta, it's like it starts at 0 and it goes up to 1 and then it goes back down to 0 and then down to -1 and then back to 0. And so it's kind of like going up and down. So it goes up to 1, down to 0, down to -1, up to 0. And it kind of does that over and over as you spin around the circle. And so that's actually, as it turns out, you know, what these trig functions look like. And so if I were to graph one of these trig functions,
I'm falling asleep over here. Do better. Also, some interstellar music would be nice with you explaining this, so put some now.
interstellar music, like from the movie, I feel like that could get the VOD muted. But maybe we could have more exciting music. What if I put on some sound Voltex music? Just make it a little bit quieter. Yeah, no copyrighted music. Can you pretty please do hyperpop? Maybe we can do a little bit of hyperpop in a minute. And so before I show this now, so once again, like think it's if we have like the sine function, so like sine of theta, then you can imagine sine starts at 0 and like it works its way up to 1 and it goes back down to 0 and then it goes down to
Don't listen
negative
to
1 and
that
back
bitch.
up to 0.
Maths are cool and interesting. Don't submit to some beta over there because they can't handle the theta males over here.
Thank you, Yeet. And so if I type in sine of theta, and then I say, let's say that's equal, like y equals that. And so you can see it. And so x, it starts at 0, and as theta increases, it goes up to 1, and then back down to 0, and then down to negative 1, and then back up to 0. And it keeps doing that over and over. It's periodic. It's like a wave. And then in contrast, cosine, it starts at 1, and then as we move up to this point, then it goes down to 0. And so now we're looking at the x-axis, so you can kind of tilt your head sideways maybe. But cosine, it moves us down to the x, like we get close down to the y-axis. And so x goes from 1 down to 0, and then to negative 1, and then back up to 0, and then back up to 1, as we kind of go around through these points. And so like right here it would be 1, here it would be 0, here it would be negative 1, here it would be 0, and then here it would be 1. And so cosine looks very similar. So if I write y equals cosine theta, then you can see when our angle is 0, then we're starting at 1, and then it kind of moves through to negative 1 and then back up to 1. What we haven't discussed necessarily is, when does like these 1s and 0s happen? And so you can see here on this graph, they have it in terms of like pies and stuff like that. And so normally whenever you might kind of normally like first learn this stuff, you might think of it in terms of like degrees. And so here, I'm going to need to change my scale. Let's do to, I don't know, 400. Or no, let's do 800. And so now the x-axis here is in degrees, as opposed to being in radians. And so you can see at 0 degrees, like our cosine function would be at 1, and then after 90 degrees, we would be at 0. And so if we think about that in terms of like our circle picture, then you can think again, it's like, okay, well, cosine and sine are like this point on our circle. And so if we start here, if this is where if this right here is where theta is equal to 0, then as it increases to 90, well, then cosine goes from 1 to 0 and sine goes from 0 to 1. And so that's what we can kind of see here. If we start at 0, then as we go from 0 up to 90, then sine, which is in blue, goes up to 1, and cosine, which is in orange, goes down to 0. And they kind of both do this periodic thing, this like wave motion. They're just like a little bit out of sync from each other. And so, it's like cosine's like a little bit like ahead of the game. Like it's already started at 1. And so I actually have another graph that I prepared for this. And so here you can see we have like a circle in the middle. And so this circle is a unit circle, and so it has a radius of 1. And I have... What's a cosine and why is it cosine? So it's just like basically saying like sine and cosine are like related. They're what we call cofunctions. And so as far as kind of like what it means to be like a cofunction, basically it's like you can just kind of think of it to mean like they're related to each other and like they're close to being the same function, but not exactly. I'm not sure if that's like, I don't know if that's really actually that close to like what the technical definition of a cofunction is, but that's like the idea. You have sine, and then you have like sine's cofunction is cosine. But so then you can see here, I have the graph for sine in orange here, and the graph for blue, or I'm sorry, for cosine in blue here. But you can see I've turned cosine like on its side. And so as I increase like theta, as I increase basically like how far we've turned from around the circle, like watch what happens to this point on the circle. And so you can see the point goes around the circle, you know, kind of like how we would expect it to. Like as you increase the angle, we move around the circle. But then you can see I've got these lines here that kind of like connect it to the same point on the graph for cosine and sine. And so you can see on the graph for cosine, wherever we're at on the circle, its x-coordinate corresponds to like this same point on the cosine function. And then same thing wherever we're at on the sine function, or wherever we're at in like the y-coordinate of the circle corresponds to like the same point on the sine function. And so this just further reinforces that like for a unit circle, then like the sine of an angle is like the y-coordinate and the cosine of the angle is the x-coordinate. And so it's just all of these facts sort of play together. Hey bro Tito, how's it going? We're going through some review of trigonometry. And then we're gonna probably spend some time looking at the preface of the book. And so, you know, one of the major things that you need to kind of like retain for calculus, you know, is this idea that of like the unit circle. And we'll also spend a little bit of time talking about like trig identities as well. Here, let me get a drink. But yeah, so at this point you might be kind of like, all right, well, what gives? Like, why do we care? Like, why do we want to know all of this? And well, I mean, in general, it's really helpful to know trigonometry because, you know, triangles are like everywhere. And so trigonometry is like one of the most useful things that you can have like under your belt in construction or anything like that, because then you can say, okay, well, if I know that the angle from like here to here is this, and that this side is this long, then I can figure out how long the other side is. And so trigonometry is just, you know, it's really helpful to kind of like put things together and kind of solve problems kind of like in space with new values that maybe you haven't been super experienced with before, you know, like using the angles of things. But one of the things that kind of comes up pretty often is like trig identities. And so there are a whole bunch of trig identities. And I think it's a lot of fun because to me, it's almost like a puzzle where it's usually like, all right, start from this identity or like start from this setup and this problem and try and like work your way through to like this new form. And so let's see if maybe we can find some like examples. And so like here would be like, you know, the trig identities themselves. How small is this? It looks terrible. Okay, let me see. Open in a new tab. Well, then I will just snip it. Okay, here we go. And so here are the trig identities. And so maybe a good thing to start with would just be like, so I will learn law of cosines and law of sines in my pre-calc classes. Yeah. And so law of sines, like there's lots of kind of like equations relating things between like different trig functions and things like that. And so here are some of them. You know, there's also like the law of sines and cosines. Law of simes. And so the law of sines, if I can like write and speak today, that would be nice. And so the law of sines basically tells us that like for a given triangle, and this specific triangle doesn't actually even have to be like a right triangle. It can be like any shape of triangle. And so it could go like up like this, and then down like this. I don't know if this triangle is going to look any good. And so, you know, for this triangle, like let's say it's not a right triangle. But one of the things that's still true, even though this isn't a right triangle, if we label it like so, where this is like angle A, and this would be side A, then this is angle B, and this is side B, and this is angle C, and this is side C, then what we can end up saying is that the sine of angle A divided by A will be equal to the sine of angle B divided by side length B, which will be equal to the sine of angle C, which will be divided by the side length of C. And so it's basically like the ratio of like the sine of the angle and its opposite side. We did this like yesterday. We did. But like the sine of the angle, and it's like the ratio of the sine of the angle and the opposite side will be like equal for all of the sides and angles in the triangle. And kind of one of the sort of things that you can sort of use to conceptualize like why this is true is that like, you know, if we just took like angle A, for instance, and so if we just kind of like think about angle A for a second, and we keep B and C the same, well then what happens if we like increase A? Like angle A. If we increase angle A, then side A has to get bigger. Like it has like they get y, like the two ends here, like this point on the triangle and this point on the triangle will be getting farther apart. It'll get like wider. And so it would go this way and this way. And then the same thing would happen if angle A got smaller. And so if we were to like make angle A smaller, then they would get closer together. And so there is something to be said just like immediately, intuitively, about like the angle in a triangle is related to the length of its side. Now we're doing ambiguous case. You guys doing the ambiguous case in trig class? Right now, actually? Yeah, I mean, this one technically would be... like this, depending on like how you're, like what perspective you're looking at it from, this could be like an ambiguous triangle. But it depends which angle is unknown. But yeah. Here, let me change this music again. I am not feeling the sound vortex. Sure, here you go. And then the law of cosines is another one that kind of works. Cosines. Law of cosines is also true, kind of regardless of what triangle you have. Like the triangle could be any dimensions. It doesn't matter if it's a right triangle. and the law of cosines still always works. And so the law of cosines, the way that I think of the law of cosines is it's like the Pythagorean formula, but like minus a bit. And so we'd have like c squared is equal to, or here, I'll write this in terms of this triangle. So we'll have capital C, and so the side length c squared is equal to a squared plus b squared. But then it's like minus a bit. And so it's like minus a portion here. And so then the question is, okay, well, like, what's this portion that goes here? And so it turns out it's going to be 2 times a times b, and then times the cosine of angle C. And so, like, what that means is if we know, like, if we know some information about, like, what this side and this side are, and we know what angle C is, then we can figure out what the side length of C is. So, like, we can figure out what side length C is. And so before, whenever you were kind of doing problems in geometry, you were limited to, like, either doing it for right triangles, where the Pythagorean formula would apply, or you were limited to, like, leveraging some other type of geometry that would work. One thing that I would like to point out is that in the case where C is a right angle, and so we would have like the cosine of 90 degrees. Well, if we go back to our Desmos graph, and so whenever we go to 90 degrees, here, let me go back to the graph we just had. Here, I will just open another one. Stop this. It's bright. Reverse contrast. So yeah, if we type in cosine of theta, so y equals cosine of theta, and we go back and we put this in degrees, and we set our scale. And so we'll go out to like 800. Then if it were a right triangle, and so if this were a right triangle where C was 90 degrees, then the cosine of 90 degrees is just 0. And so in the case where this is a right triangle, well, then the law of cosines just simplifies down to be the Pythagorean formula. This portion here becomes 0. And so, this is like, we can say that this portion is equal to 0 when C equals 90. And so this is like another case where you could just say, okay, well then the law of cosines is just like or the Pythagorean formula in this case is just like a special case of the law of cosines. Okay. Well, so that's neat. And so let's start with some of these trigonometric identities. And so a couple that I just want to kind of, talk about really quick. And so these like top 3, we've already sort of talked about these 3 to an extent. We've talked about the Pythagorean identities. We haven't talked about either of these 2. But if we kind of look at this for a little bit, and so we know that tangent of theta is equal to like our opposite over our adjacent. And then we know that sine of theta is our opposite over our hypotenuse, and that our cosine is our adjacent over our hypotenuse. And so one thing that you might notice is that, okay, well, we have our opposite over our hypotenuse and our adjacent over our hypotenuse. And here we just have our opposite over our adjacent. And so one thing that we could do with the formula for tangent of theta is if this were instead like our opposite over our hypotenuse, all over our adjacent over our hypotenuse, then this would still be true. The hypotenuse, like in the denominator on the top and bottom, like could both cancel each other out. And so then what we can kind of ultimately see here is that, you know, our top, we could write this as sine theta over cosine theta. So one thing I've always wondered is how the calculator performs the trig function. So that's actually a really great question. How do you get from sine of 90 to 1? So there are probably some values where it just knows them. So such as like sine of 0 is 0, sine of 90 is 1. But the way that it actually calculates like the precise values of like certain trig functions, and when I say precise, I mean like, you know, to a certain decimal place, is it uses something called the Taylor series, or perhaps the Maclaurin series. And that is actually something that we'll probably get to, that we might get to. But basically it turns out there's like a way that you can use like derivatives and things like that to approximate functions. And then you just like, it's an infinite series and you just add on as many terms as you need to basically like make that series true. And so basically like trig function, like they're kind of cheating a little bit, but they just like are doing enough iterations of this Taylor series or this Maclaurin series until they have like enough like decimal places down to like a precise value that they can tell you confidently that like the sine or cosine of this value is equal to this out to the 12th decimal place or whatever. And so really like calculators are just like approximating trig functions for the most part. Other than for probably like specific values where like the specific values are known. How did we find the Taylor series? So we'll get to it. And so it's kind of like putting the, you know, cart before the horse a little bit, because the Taylor series includes derivatives. And so like the derivatives are something that we're going to talk about in calculus. But the very, very short version, perhaps to sate your curiosity for now, is that like the Taylor series is like what happens if you do like linear approximations with like nth order derivatives. And so like you can approximate something with like a single derivative, kind of like locally, but then as you add more and more derivatives around that point, you get more and more accurate further and further out. And then eventually, if you were to do it infinitely many times, so kind of adding on infinitely many derivatives of the function, you would actually get the exact function. Like you can describe any function that's differentiable as basically like an infinite series. Well, we're gonna miss surprise VIP. No one's gonna get it. Bum, 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 bum. Bam. So kind of this is what we got here. And so we can say that tangent of theta is sine theta over cosine theta. There are some other effectively like definitions that we can get here too. And so just like there's tangent, sine, and cosine, there are actually a couple other trig functions. And so we have like cotangent, cosecant, and secant. And so those would be like, you know, secant spelled like this. And so there is, I think, like geometric interpretations of kind of like what all of these things sort of like reference, like specifically, or kind of like what lengths or like what ratios they are. But I just know them kind of like in terms of these here, they're reciprocal identities. And so, you know, sine and cosine, they're technically like two completely different functions. Tangent and cotangent are actually like reciprocals of each other. And so one of the ways that you can get cotangent, often written like cot of theta, is it's going to be 1 over tangent of theta. Hey, Horse Sniffer, you got a math question? What's your math question? And then we can also say that, and so, best way to do my taxes, but with shapes and colors. I don't even know how really to do my taxes. That's like an accounting question. I feel like you just need like a magic spreadsheet. So there is like, and so sine and cosine are co-functions of each other. Presumably tangent and cotangent are co-functions of each other. Once again, I don't really know, I think, exactly kind of what that means for like functions to be co-functions. But the way that we define secant, and so just sec of theta, so secant of theta is 1 over cosine of theta. And then cosecant, CSC of theta, is 1 over sine of theta. And so there are effectively like variations on different identities using like cosine, sine, and tangent, or cotangent, secant, and cosecant. And so like one of the things that we can like talk about, like, you know, we did this one up here where tangent of theta is equal to sine theta over cosine theta. Well, we can also show that cotangent of theta is equal to cosine over sine theta. And so if we have cotangent of theta is equal to 1 over tan theta, then this would be equal to 1 over sine theta over cosine theta. And you might remember that if you divide by a fraction, one of the things you can do is like keep, change, flip, where this would end up being like, we keep the 1 on top, we change this division to multiplication, and so this would be times, and then we'd flip the bottom. And so cosine theta over sine theta. And 1 times anything is itself, and so we would have cosine of theta times sine theta. Or I should say 1 times anything is whatever that anything is. 1 multiplying by 1 is the multiplicative identity. But yeah, so that tells us that cotangent of theta is cosine over sine. And what we showed earlier, where we could say that like sine squared of theta plus cosine squared theta, that's also an identity. And so this one's called the Pythagorean identity, because it's derived from Pythagoras' formula, or the Pythagorean formula. Kind of like combining those ideas about like, you know, if you have like a circle with a radius of 1, then, you know, like sine and cosine correlate to like the x coordinate and the y coordinate. And so that's how kind of like the Pythagorean identity sort of falls out of that relationship. But we can also like manipulate this algebraically to get kind of like other variations on the Pythagorean identity. One way that we could do that is, okay, well, what happens if we divide everything by sine squared theta? So we divide this by sine squared theta, we divide this by sine squared theta, we divide this by sine squared theta. What do we get? Well, sine squared theta divided by sine squared theta is just 1. cosine squared theta divided by sine squared theta. Oh, well, that's going to be cosine. So like, okay, maybe let's take this to the side and we'll kind of break that down really quick. And so cosine squared theta divided by sine squared theta. And so mentioned it briefly earlier, but this is just kind of like notation for like sine squared theta is just sine theta all squared. And so this would be cosine of theta over sine of theta. And if the top is squared and the bottom is squared, well, this can just be all of this squared. And hey, cosine over sine. We just talked about that. That's equal to cotangent. And so we can have another variation on the Pythagorean identity, which would be 1 plus cotangent squared. And then this would be 1 over sine squared. And then 1 over sine is cosecant. And so this would be cosecant squared theta. Okay. Well, what if we do that again, but we divide everything by sine squared instead, or cosine squared instead? So if I divide this by cosine squared theta, and then this by cosine squared theta, and this by cosine squared theta, well, sine squared theta divided by cosine squared theta, doing kind of the same thing in the same logic, is going to end up being tangent of theta squared, since tangent of theta is sine theta over cosine theta. And so this will be tangent of squared theta, and then plus cosine squared divided by cosine squared. Well, anything divided by itself is 1. And then 1 over cosine squared. So 1 over cosine squared is going to be secant, because 1 over cosine, or it's going to be secant squared, because 1 over cosine is secant. And so this will be secant squared theta. And so one of the things that, you know, I always kind of use to help myself remember these, at least to a certain extent, or at least that I thought was helpful for me, is a lot of the times with these trig identities, the way that they often work out is that, like, you know, you can see for this one we have cotangent and cosecant, but on this one we just have normal tangent and normal secant. Now that's not necessarily true for just like the bog standard Pythagorean identity, because for that one you have sine and cosine, but it usually seems to work out the way where if you have like sine and cosine, then like those typically kind of go together in a certain way. But for the other types of identities you often see, then, you know, it's usually like you have tangent and secant go together, and you have cotangent and cosecant go together. And that will be helpful for later on too. And so, one other thing that I want to talk about, actually there are other trig identities too. Yeah, let's grab this sheet. Snipping. Okay, and so here's a list of a bunch of different trig identities. And so there's actually like a pretty good way to sort of figure out like what a lot of these identities are. And so I remember like whenever I was kind of like initially taught how to do these identities, like it just felt like you had to memorize them. And memorizing some of them was really weird. Like if you look at these sum and difference identities, or like the half angle identities, or like the double angle identities, like just like any of these ones down here, effectively, like end up being very strange. And one thing that I like that really helped me kind of like understand them and to figure them out was to actually figure out how to derive them. And so, but the way that you have to derive them is by using this thing called Euler's identity. And so if you're here because you're a math enthusiast, you've probably heard of Euler's identity before. But if you haven't, then allow me to introduce you. And so Euler's identity says that basically if you have e to the I theta, I saw it in a stick figure video. Yeah. And so if you have e to the I theta, then this will be equal to the cosine of theta plus I times the sine of theta. And so I is the complex number, I. And so I is equal to the square root of -1. And so ordinarily you can't take the square root of a negative number because in theory it just doesn't really make sense to kind of like pose the question of like what is the square root of a negative number? Because, usually when you say like what's the square root of 4, for instance, well, the square root of 4 is 2, but that's because 2 times 2 is 4. But what times itself is -1, or any negative number, for instance. I mean, 1 times 1 is 1, and -1 times -1 is also 1, because a negative times a negative is a positive. And so how do we get, how do we take the square root of a negative number? It doesn't seem possible. Well, it turns out it is simply if we kind of like devise a new way to describe them. And so that's where this variable I comes in. And so if we say that I is equal to the square root of -1, well then we can say things like I squared would then have to be equal to -1, because the square root of something times the square root of the same thing has to be whatever you're taking the square root of. It's like saying the square root of 2 times the square root of 2 has to be equal to 2. The square root of -1 times the square root of -1 will be equal to -1. And then we can go on to say things like, I to the power of 3. Well, that would be I squared times I. And I is -1, and so that'll be -1 times I. And so I to the power of 3 is -I. Or I to the power of 4, well, that would be I squared times I squared, which will be -1 times -1, which will be 1. And you can actually keep going. And so then if we had like I to the power of 5, well then this would be I to the power of 4 times I, and I to the power of 4 is just 1. And so we have like another periodic relationship where, if we go from like I to I squared to I cubed to I to the 4th to I to the 5th, it's like, it comes back to the beginning. And so, as we were talking about earlier, like with the trig functions and stuff like that, these trig functions are also periodic. And so while this doesn't necessarily help maybe give you like a full, like it doesn't comprehensively or rigorously help you understand why something like the Euler's identity is true, you maybe can be convinced that there is this idea where since like powers of I are periodic, and then there's this something that's like oddly periodic about like, or that like moves in a cycle about like the value of I. And so, it makes sense that something like e to the I times theta could be related in some way to trig functions, which are also periodic. And so it's not like a very great explanation for like why it's true, but part of why I want to what I'm here to do is maybe to just kind of help give you intuition about certain things. And I feel like it's something that's like like a relatively intuitive thing that maybe you can connect. But at any rate, we have Euler's identity. It allows us to make a connection between this exponential function, e to the power of I times theta, and these trig functions. And well, there's a lot of things, like there's more things that we can do with exponential functions than we can with trig functions. And so you might remember kind of just like some of the properties of exponentials that we have. Like if we have x to the power of a times x to the power of b, that gets us x to the power of a plus b. Or if we have x to the power of a all to the power of b, this gets us to x to the power of a times b, and so on. Or if I had, and this would even let me say things like if I had x to the power of a divided by 2, well, this would be the same thing as x to the power of a like times 1/2, which would be like x to the power of a all to the power of 1/2, which if you remember how rational exponents are like actually like the same thing as like square roots and stuff like that, would tell us that this would like x to the power of a over 2 is like the square root of x to the power of a. And so, but point being, there's lots of things that we can do with exponential functions using kind of like the properties of exponentials that we have. And so maybe that would let us kind of start to do different things with like trig functions too. If we kind of like examine what types of different setups we can have with Euler's identity, and then kind of see how that affects the trig functions on the other side. And so, for example, like one of the identities we have here is the sum and difference identities. And so if we look at these, they're a little bit complicated, where you have like the sine of an angle plus or minus a different angle. It's like the sine of theta times the cosine of phi plus the cosine of theta times the sine of phi, and all of that stuff. And then you have to try and remember, it's like, okay, when does the sine and the cosine go together versus when do the cosines go together? And am I adding them or am I subtracting them? Or like what even is the formula for the sum and difference identity for like tangent and all that stuff? And so I always have a hard time remembering them. But for me, it always helps to know how to derive them, to know where these formulas come from. And so let's examine the sum and difference identity first. And so sum and difference. And so for the sum and difference, basically like we're wanting to know what happens if we have two angles and we're adding or subtracting them from each other. And so if we were to start with Euler's identity, but we were to replace it with e to the I, and then replace our theta with the sum of two different angles. So we could do alpha plus beta. And so we have e to the I of alpha plus beta. Well, we could rewrite this using one of our exponential identities as, you know, if we have alpha plus beta, well then this can be e to the I times alpha times e to the I times beta. And so this would be e to the I alpha times e to the I beta. And now we can apply Euler's identity. And so this e to the I alpha here, this will be the cosine of alpha plus I sine alpha. And then e to the I beta will be the cosine of beta plus I sine beta. And so now we have this times this. And so these are being multiplied together. And so then we can FOIL this out like we are known to do with binomial terms being multiplied together. And so if we have cosine alpha times cosine beta, well, the angles inside of them are not the same. And so I'll just write that as cosine alpha times cosine beta. Then if we have cosine alpha, here I'll use a different color. Then if we have cosine alpha times I sine beta, well then this will be plus plus I of cosine alpha times sine beta. Then if we multiply these together, so I sine alpha times cosine beta, and then I sine beta times I sine alpha. Well, then for I sine alpha times cosine beta, we get plus I sine alpha times cosine beta. And then for I sine alpha times I sine beta, we get I squared times sine alpha times sine beta. And so far, these are all like equal to each other. These are all equal statements. So this is equal to this is equal to this and all that stuff. Hey, Femvox fan. And so, but this looks kind of gross. And so maybe we should do like a little bit of simplification for this. Well, as we just discussed previously, we know that I squared is -1. And so we can simplify this, and so I'll put all the terms with I kind of over on one part, and then everything without an I on the other part. And so these both right here, after we make this into -1, will both not have an I. And so I'll write this as cosine alpha times cosine beta. And then this will end up being minus sine alpha times sine beta. And then these ones here are still going to have an I in them. And so then I'll write this as plus I times, and then this will be sine alpha times cosine beta, and then plus sine beta cosine alpha. Okay, well, cool. So what? And so what we said earlier is that, okay, well, perhaps another thing that I should mention here, if we come back in up here and we just take this part, then we can still apply Euler's identity to this, where if theta is alpha plus beta, then we can also say that cosine of alpha plus beta, or that this would be equal to cosine of alpha plus beta plus I times sine of alpha plus beta. And so now the magic comes in where, you know, we took this and we went through one route and we went through all this stuff and we did all this and we got down here. But if we just did this right at the beginning, well, we would get this. Well, regardless of the fact, that means that these two are equal to each other. And so that means that cosine of alpha plus beta plus I times the sine of alpha plus beta that these are equal to each other. Well, what are we supposed to do with that? Well, you can see that what we have here in orange is everything that like isn't complex. It doesn't have like it's the real portion of this like complex number. Whereas everything over here in gold has the I attached to it. It's what we call like the imaginary portion, because I is very poorly named as the imaginary number. Not to say that they're like fake. That's just what they've always been called. And so usually it's like if you have like a number that has like a real portion and an imaginary portion, we call them complex numbers. Only that part is real, so only that part matters. Duh. Hashtag pwned. Hashtag owned. I have been pwned and owned. I will never financially recover from this. But what this lets us do is it kind of lets us like make the same sort of comparison over here. This portion right here is the same, where it's also the real portion, where it doesn't have any imaginary part of it. And this part here is also the imaginary portion where it has the I attached to it. And so what we can actually say then is that, you know, for these to be equal, then essentially their real portions have to be equal and their imaginary portions have to be equal. And so then ultimately what we've shown is that cosine of alpha plus beta, this here, is equal to this here. And so cosine of alpha times cosine of beta minus sine of alpha times sine of beta. And then same thing, we've shown that this and this are equal as well. I'll draw that a little bit better. And so this would be sine of alpha plus beta is equal to sine of alpha times cosine of beta plus sine of beta times cosine of alpha. And so that proves the sum and difference identity. And we can do something very similar for the other identities too. I think we should go through them. I think it would be fun. And so for the other identities, so this was like the sum and difference identity. And so we wanted to show that two angles added together, have this relationship with the trig functions. And so what's another identity? Well, we also have the double angle identities. And so if we start again with our Euler identity, and so we want to know what happens if we double the angle. Well, this would be e to the I of 2 theta, which, just following the standard Euler identity, would tell us that cosine of 2 theta plus I sine is equal to I sine 2 theta, or cosine 2, e to the I of 2 theta. What am I saying? E to the power of I times 2 theta is equal to cosine of 2 theta plus I sine 2 theta. And so that much we know is true. That just falls out of Euler's identity. But we know that from our exponential identities, again, if we have x to the power of a times b, well, then we can basically turn that into x to the power of a all to the power of b. And so we can turn this into e to the power of I to the power of theta all to the power of 2. Which would tell us that this would be the cosine of theta plus I sine theta all to the power of 2. I had a physics professor say effectively that. I just wanted to say in context of simple harmonic motion when re-examined with differential equations, but it's been years at this point. Yeah. It turns out math really is complex sometimes. Not that it means it's complicated, just means it's complex. But yeah, welcome Zionth. So yeah, from from here, we can take this and we can expand this out. And so this will be cosine of theta plus I sine theta times cosine of theta plus I sine theta. And now we can FOIL. And so this times this, this times this, this times this, this times this. And in the end, we'll get cosine squared theta. And then plus I sine theta times cosine theta. But we'll get that twice, because then we get cosine theta times I sine theta. And so I'll write this as plus I times 2 sine theta times cosine theta. And then I sine theta times I sine theta is going to be plus I squared sine theta squared theta. And again, I squared is equal to 1, and so this will become -1, and then we'll write the real portion over here. What are we listening to? Hello? My ears. Excuse me, Spotify. And so if we rewrite the real portion on one side and then the imaginary portion kind of towards the other side, then we get that cosine squared theta minus sine squared theta is over here as kind of like our real portion. And then we get I times 2 sine theta cosine theta. And so once again, we can do the same thing that we did earlier, where if I take this, put it over here, take this, copy it here, then you can see this portion here is our imaginary portion, and this portion here is our real portion, and then the corresponding imaginary and real portions have to be equal to each other. And so what this means then is that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. And so so you see like cosine squared theta minus sine squared theta, it's very close, but it's not the Pythagorean theorem, or not the Pythagorean identity. And so just remember that cosine squared and sine squared have to be added together for the Pythagorean identity. And then sine 2 theta is equal to 2 sine theta cosine theta. You're doing a great job here, by the way. Using Euler here really helps, and your explanations I've caught have been super clear. Awesome. Hopefully I can keep that up. But yeah. And so let's see. But yeah, kind of the long and short of it is that you can use like Euler's, like doing now the half angle identity would be very simple, except instead of substituting like 2 theta in and applying Euler's identity, we would substitute in theta over 2. And then once we have it, like, then it would be in terms of like sine squared is equal, like sine squared of theta over 2 is equal to 1 minus cosine of theta over 2. You know, maybe I should just show it. I'll just go through each of them. And so you know it, you love it, Euler's identity. We have e to the I, and now we're going to do theta over 2. And so that would tell us that this is equal then to cosine of theta over 2 plus I sine of theta over 2. And so then we go through the kind of whole process again. You know, kind of like what I showed up here. The reason why I showed this example is, you know, basically like we can make this all to the power of 1/2, which would be like taking the square root of it. Or, let's see, is that actually how I want to go through this? Because oh yeah, and I should mention too, you know, once you have something like the sum and difference or like double angle formulas, then you can just do like sine of 2 theta over cosine of 2 theta to get like tangent of 2 theta. And then you can fill in kind of like the respective like identities that you've already found and simplify. Let's see, is this how I would do this one? Maybe the way that I'll do this one is to think of this as being, instead of e to the I of theta over 2, let's think of this as e to the I of theta minus theta over 2. Is that going to work? Because theta minus theta over 2 I'm trying to think. Because theta minus theta over 2 will be theta over 2 and sine of theta over 2. And so if I were to split this up, this would be e to the I theta. You can just apply the half angle identities here, right? Well, so what we're trying to do here is like to use Euler's identity to show the half angle identities. And so we're like proving the half angle identities here. At least that was the idea, you know, because like for me, the thought process is always like, sure, I can like memorize formulas, but if I understand where they come from, maybe it's that much easier to memorize them. And so I wanted to show the proof with the half angle identity. Because I don't really know, I think, what I would do with like the square root of all of that stuff. So let's try it like this, maybe instead. Because then this would be times e to the power of negative I of theta over 2. And then I could rewrite this as e to the I theta over e to the I theta over 2. And then I could evaluate the top and then evaluate the bottom in terms of like the Euler identity. Because then this would be cosine of theta plus I sine theta. But then this would all be like the over 2 here would make the bottom like the square root. I don't know, maybe it's not as simple as I realized. Because they end up with sines. Okay, I get it. Actually, I should not have been so deterred to take the square root. And so if we have e to the I of theta over 2, well then we could rewrite this as e to the I theta all to the power of 1/2, which will ultimately be like the square root of e to the I theta. Which would give us basically the square root of cosine of theta plus I sine theta. And so ultimately that's what e to the I of pi over 2 is equal to. And then so what we can now say then from here is if we, and then so basically like what we've said now is that cosine of pi over, or theta over 2 plus I sine theta over 2 is equal to e to the I of theta over 2, which is equal to the square root of cosine theta plus I sine theta. And so if we just square everything, and so if I square all of this, and I square all of this, and I square all of this, then I think we'll be on the right track. Because then after squaring everything, we get cosine of theta plus I sine theta. And then it'll be equal to this all squared. And so we'll have cosine of theta over 2 plus I sine theta over 2 times this times 2. Well, not times 2, but like we have 2 of them. And so we FOIL that out. And so we'll get cosine of theta plus I sine theta is equal to, and then we FOIL this out. And so this will be cosine squared theta over 2. And then we'll have these imaginary terms. And so then I times 2 sine theta over 2 cosine theta over 2. And then plus I squared sine of theta, sine squared theta over 2. And so then now we can do what we've been doing. The I squared becomes minus 1. And so let's see. And so then I think the idea here is then like you can substitute. So let's see. If we have no, because now if we make this substitution and set this equality up this way, we just get the double angle identity again. I guess it is to say that you can use the double angle identity to find half angles. Replacing cosine squared with 1 minus sine squared seems good. Yeah, I guess now we could apply like the Pythagorean identity. We get that one pretty immediately. Yeah. And so if we do make that replacement, and so we can say by the Pythagorean identity, which the Pythagorean identity says, once again, that it's sine squared theta, whoopsies, sine squared theta plus cosine squared theta is equal to 1. And so by subtracting cosine squared theta from both, or sine squared theta from both sides, we can say that cosine squared theta is equal to 1 minus sine squared theta. And so that would make this 1 minus sine squared of theta over 2, which would get us 1 minus 2 sine squared theta over 2. Well, this is just another... Wait, are these not just the double angle identities? We were trying to get the half angle identities. I mean, I guess the double, like, it's the half angle and double identities are just like these rearranged. I guess I'm overthinking it. Because, you know, if we have cosine of 2 theta is equal to 2 times the cosine squared minus 1, then you add 1 and then divide everything by 2. And then you just substitute 2 theta for like theta. And then the other one would be theta over 2. I guess proving the double angle identities proves the half angle identities simultaneously. Okay. Let's see. What else did I have on the docket? Polar coordinates? Should we talk a little bit about polar coordinates before we get into the book? See, we're coming up on about 2 hours now. And so polar coordinates, so up to now in math, we've mostly been talking about like graphing things in terms of X and Y. But it turns out there are lots of other ways to graph things. And so whenever we kind of talk about like the rectangular coordinates, kind of like the basic way to describe it is you have a point in the grid that we describe as having the coordinates of x comma y, where x is the distance we've traveled horizontally from the origin, and y is the distance we've traveled vertically from the origin. But there are other ways that we could choose to like define where a point is in the grid. Other ways to kind of go about it. Big Chuck, thank you for the follow. Welcome in. The Chuckster. Sorry, maybe I shouldn't call you the Chuckster. Anyways, so another way that we could kind of talk about where this point is that would kind of contain all of the same information is what if instead we described this point as being some distance away from the origin? And so rather than it being X and Y, where it's horizontal distance and vertical distance, we could say that it's just this distance R, or D. Yeah, I'll say R from the origin. Hello, Talos. I am home, meow. Shall I hang out here? It's up to you. If you want to join in, we're actually gonna, be doing questions from the book in a little bit here. But I'll leave it entirely up to you. We've spent some time kind of talking about trig identities and where they come from, and trigonometric functions and like the law of sines and cosines, just kind of all like briefly. And I wanted to touch a little bit on polar coordinates. I shall pour one wine and hang out in VC. Okay. Sounds good. Let me see. I'll go hang out in here. So, polar coordinates. So it's another way that we can kind of describe where a point is in the grid. And so rather than it being like horizontal distance and vertical distance, we can just say direct linear distance between some point and the origin. And then we can use the angle as measured from the positive x-axis. And so this means for like every point in the coordinate plane, you can think of like a right triangle that would describe that point, and then we can describe those coordinates as like some like manipulation of trig functions with r and theta. And so, for instance, if we had, let's say, like as an example, if we had a point down here that was, how do I want to do this? If this coordinate was at 3, 4, and so it would look more like this. It'd be stretched out a bit vertically. And so if this is at 3, 4, then what we can say is that, you can essentially like effectively imagine a right triangle where the base of it down at the bottom here is going to be 3 and the height is 4. And then if you knew your like special right triangles, then you would know that this hypotenuse here is 5, because 3 squared plus 4 squared will be 9 plus 16 is 25, and the square root of 25 is 5. And then this would still be our angle theta. And so then what we know is that this point in rectangular coordinates is 3, 4. But, for this, we could say that basically like that the sine of theta would be 4 over 5, and that the cosine of theta would be 3 over 5. And so one thing that we could do is multiply both of these sides by 5. And so we would get 5 times sine of theta is equal to 4, and 5 times sine of theta is equal to, or cosine of theta is equal to 3. And so then what we can say then is basically like, that's 5 times the cosine of theta is equal to 3. So like that's also this horizontal distance right here. And so this is the same thing as 5 times the cosine of theta. Or 4 right here is also equal to 5 times the sine of theta. It's kind of like a way to get that horizontal, like that vertical distance or that horizontal distance again, essentially. And so like you can convert back and forth by like describing something with like either its radius or like basically like its distance from the origin with its angle or its rectangular coordinates. It's like you can convert back and forth. And so like this point could be x comma y, or we could describe it as r comma theta. And if you need to know what that is in rectangular, you can like convert forwards and backwards using the trigonometry. Usually the kind of way we describe it is that like x will be equal to r cosine of theta, and y will be equal to r sine theta. And so then one of the things that's, interesting is if we kind of go back to like the Pythagorean identity, if we have x squared plus y squared, then that would give us x squared plus y squared would be equal to r squared cosine squared theta plus r squared sine squared theta. And then you could factor out the r squared, and you'd be left with cosine squared theta plus sine squared theta. And by the Pythagorean identity, cosine squared theta plus sine squared theta is just 1. And so, in other words, x squared plus y squared is equal to r squared. And hey, that looks kind of familiar. Where have I seen that before? Oh, it's the equation of a circle. And so it all comes back around. And so like all of these things that, maybe on the surface don't necessarily seem like directly related to each other are in fact all like inextricably related to each other and combined together in a whole bunch of different ways. Hi, Pen. Did I move you in too early? I'm good. How are you? Yeah, how was bingo? Yeah. I guess that's why it ran a little bit late, right? Something along those lines? Mm-hmm. Well, cool. And so we have been talking about trigonometry in here. Trigonometry, which as everyone knows is the study of circles. Is that correct? I think it's supposed to be the study of triangles. That's trigonometry. And so on my list of things that I kind of wanted to get to today, we talked about trig functions and ratios, the Pythagorean formula, and how it relates to the Pythagorean identity, the equation of a circle and where like the equation of the circle like comes from and how does that relate to trigonometry. We talked a tiny bit about law of sines and cosines because there were some questions about that, and then we started going through like all the identities. and like showing where the identities come from with Euler's identity. And I just talked briefly about like polar coordinates too. Yeah. I mean, like, you know, complex numbers are usually something people like have access to. So I did a very hand wavy sort of explanation as to like why Euler's identity is true, or why you might feel like it's true. So I had originally been going to school for electrical engineering, and then eventually decided that engineering's not what I wanted to do. And so I am going back to school to finish out a degree in math, but I already have a minor now, thanks to that, in engineering physics. Oh yeah. So much. Well, I've turned coat, right? I've turned coat from engineering to, and you know, frankly, that was the straw that broke the camel's back. Once they were like, hey, we're gonna write it as J now. And I was like, oh, sorry, I'm out. That's what I did in undergrad. Yeah, and so, I mean, I don't know that there's too much else. I mean, like, you know, we're kind of glossing over some things here, like actually like evaluating trigonometric functions, and like, you know, I haven't quite gotten to like inverse trig functions and stuff like that. And so, but I just don't know like how much really to like get into it. And so like kind of like I did spend some time kind of going through the preface of the book, kind of like seeing like, all right, well, what are they expecting us to kind of know and kind of be ready for? And they do have a little bit of trigonometry here. Like I did talk about how like the unit circle and stuff like that. And like the trig functions themselves, and I used that Desmos graph that I showed you. And so, thank you. But you know, it's just kind of like I'm wondering, like, should we kind of like get into it now, or kind of start going through the preface and go through questions and maybe like hit it as we go if people have questions about it and they're not sure? Because I mean, like we're coming up. Right. Okay. Well, so then I think that's mostly kind of what I was looking for in terms of the trig review. And so maybe now we can just spend the rest of the time, if anyone has any questions, of course, I'm happy to answer questions. Or we can just start kind of going through some of the review exercises from the book. And so for anyone who doesn't know, we're using Ron Larson and Bruce Edwards's Calculus of a Single Variable, 10th edition. And so, you know, well, there's actually an 11th edition, I believe, but we're using the 10th edition. I think I used one of Larson's books in like one of my classes when I was taking calculus, and I like Larson's, you know, how he goes through things pretty well. Mm-hmm. I like bees, not like this. But yeah, so I guess let's just start going through the preface, and we'll look at the review exercises, and we'll just kind of hit things as they come along. And so this will kind of be another review of everything that we've done up to this point. And so, you know, we'll just go through like each little subsection and do a question, or if there looks like one that's interesting, you know, we'll do multiple. I stopped learning after geometry. This is all very interesting to see. Well, interesting is good. So let me add another page here. And like they said they stopped learning after geometry. And so that doesn't mean that they haven't taken anything higher, hypothetically. But I just meant maybe they didn't retain anything, but I don't know. But I like that interpretation too. Maybe that what they're saying is they're actually an algebraic geometer. Yeah, I'm pretty sure they're not real. Okay, and so we got the preface questions here. And so first question that we've got, first little subsection that we've got here is to find any intercepts. And so, ooh, why did I move my board? And so first one that they've got here is, let's look at this one first. And so we've got y equals x squared minus 8x plus 12. And so they're telling us to find any intercepts. So that would be where this function intercepts the x-axis. Or I guess when they say intercepts, it could be y-axis too. And so let's make two little labels here. We'll have y-intercepts and x-intercepts. And so one thing that you could ask yourself is like, okay, well, if we're intercepting the y-axis, that means we're hitting the y-axis. And so like, what does that mean? If we're on the y-axis, that means our x value has to be 0. And so pretty straightforward, at least for finding the y-intercept. You just set x equal to 0 and see kind of what falls out of it. And so if we plug in 0 for x, then we get y is equal to 0 squared minus 8 times 0 plus 12. And so that tells us that we have a y-intercept at 12. Because 0 squared is 0, and 8 times 0 is 0. And something very similar, at least along the same lines, is true for the x-intercept. If we're intercepting the x-axis, that means our y value has to be equal to 0. And so if we set y equal to 0 and take a look at this, well then we get 0 is equal to x squared minus 8x plus 12. And this is like a classic factoring problem now. And so we have like an x squared term and we have just like a normal x term. And so we can't simply isolate the x values and find like what is x equal to explicitly without maybe doing something slightly more creative. And so we reviewed factoring last week. And so what we're effectively looking for now is what multiplies to 12 and adds to make -8. And that would be -6 and 2. And so we can say that x minus 6 times x minus 2 are all equal to 0. And then for this to be equal to 0, basically what we really care about is when is this portion right here equal to 0, or when is this portion right here equal to 0, or like, yeah, like this, the whole portion entirely. Because if x minus 6 is equal to 0, then it doesn't matter what x minus 2 is, because 0 times anything is still 0. Whereas if x minus 2 is equal to 0, then the same thing is still true, where it doesn't matter what x minus 6 is, because 0 times anything is still 0. And so based off that, we can then set these both equal to 0 individually. And so we would get x is equal, or I should write it like this. X minus 6 is equal to 0, and then x minus 2 is equal to 0. And so that tells us that x is equal to 2 positive 2, and positive 6 are our x-intercepts. And so another question on here for finding intercepts is this one here. It says y is, and so this here I should write, this was question 2. This one's question 3. And so they've got y is equal to x minus 3 over x minus 4. And once again, they want us to find the intercepts. And so for the y-intercept, we'll just set x equal to 0. And so that will be negative 3 over negative 4. And so we get an we get a y-intercept at 3/4, and so it'll be 0, 3/4. If we want to find the x-intercepts, so we set y equal to 0, and so then we get 0 is equal to x minus 3 over x minus 4. And so this one is a little bit different. Or at least it's different in the sense that you might see this x on minus 4 on bottom and not necessarily know what to do with that. And so in this case, it's actually very easy. You can just multiply both sides by x minus 4. And, well, x minus 4 times 0 will be 0. And so we've effectively canceled out the x minus 4. There is an asterisk here, though. There is something that we have to be careful of. And that basically, even though we've eliminated the x minus 4 from the denominator, we actually have to be careful to make sure that x minus 4 isn't equal to 0. Because if it were, then that means in our original function, we would divide by 0. And so if we're dividing by 0, that point wouldn't be defined. And so it certainly couldn't be an intercept. So we just need to keep in mind that whatever we get out of solving this, that x cannot be equal to 4. Because if x were equal to 4, then we would divide by 0 in our original function. But at any rate, what we're left with after that step is x minus 3 is equal to 0, and then x would then be equal to 3. And as it turns out, 3 is not equal to 4. And so we're all good. And so then we would get an x-intercept at 3, 0. At least I'm pretty sure that 3 isn't equal to 4. Right. Okay. And so here's an interesting question. So for questions 5 through 8, it says, test for symmetry with respect to each axis and the origin. And so I guess would that be like checking if they're even, odd, or neither? Or I guess if it were even, that would mean it's symmetrical. And so it's basically, is it even or not? I didn't, and so perhaps now is a good moment to hit on that. And so, so there's a couple extra ways that we use to kind of like define functions. And so for some functions, we can say that a function is even, odd, or neither. And so what it means for a function to be even, odd, or neither is relatively straightforward. And so for a function, if we have like here, if I go back over to Desmos here, and so if a function is like symmetrical across the y-axis, then we usually say it's even. So we would have like, if we had like y equals x squared is kind of like a classic example. And so if you were to like cover one eye and then just look at half the screen, or I guess cover half the screen, because covering just one eye maybe wouldn't be good enough. But if you were to just look at like but if you look at just like for the right half of the parabola for instance, then you can mirror that over the y-axis and see that it would map directly onto like the other half of the parabola on the other side. And so this would be like an example of what we call like an even function. And so the way that we kind of describe that process mathematically, how we go from like, okay, well, it reflects across the y-axis, but how do we show that like with math? And so if we describe it as a function, and so we have f of x is equal to x squared, then the way that we can reflect it across the y-axis is essentially by like negating our x values. And so like if we make all of our x's negative, then that's kind of like flipping the x-axis, or like flipping our domain, you know, however you want to think about it in terms of that. And so, but if it's symmetrical, then if we flipped our x-axis, if we flip it around, then if it's symmetrical, it shouldn't change. And so if I make this f of negative x, and I figure out what this is equal to, well, then this will be negative x all to the power of 2. And then this would be negative x times negative x, which is just going to be positive x squared again. And so in this case, we would say that f of x is the same thing as f of negative x. And that's the definition for an even function. And so this would be even. And so when f of x is equal to negative x, we say it's even. Or if you know a function is an even function, then you can also know that f of x would be equal to f of negative x. An example of a function that would be odd would be like y equals x to the power of 3. And so y equals x to the power of 3 is different in the sense that like you can see that this right side here looks the same as this left side down here, except this left side is negative. And so basically what we say for odd functions is that if f of x is equal to negative, or if f of negative x is equal to negative, or what is it? F of negative x is equal to negative f of x, or something like that. Or f of x is let me write it out. I'm getting my words mixed up. So like a function that's odd, so like if we had f of x is equal to x cubed, then if I were to plug in f of negative x into this, then we would get negative x all to the power of 3, which would end up being negative x times negative x times negative x, but 2 of those negatives would cancel out, and so I'll just write that this is negative x cubed. And so then what we can say then is that f of negative x is equal to negative f of x. Or you could move from this form, you could move this to the other side, where you could say then that f of x will be equal to negative f of negative x. And so basically then what this like means graphically is that for an odd function, you can flip it across the like the y-axis and the x-axis, and then it will map back onto itself. It's like symmetrical that way. And so like if we took x to the power of 3 and we flip it across the y-axis first, and so that would be y equals negative x to the power of 3. If we flip it across the y-axis first, and then we flip it across the x-axis, then it maps back onto itself. Yeah, because if you imagine taking like this point here at like 2 comma 8 and rotating it 180 degrees through the plane, then it would move down to -2 comma -8. And so I think the transformation of any point being rotated 180 degrees around the origin is like going from x comma x to, or x comma y to -x comma y, or comma -y. And so I do think that's, or well, so at least, and then just like negating the x value and negating the y value is equivalent to that reflecting across the x-axis and then reflecting across the y-axis. Right. Right, so rotating something 180 degrees is equivalent to just going from x comma y to -x comma -y. And that is what flipping across the y-axis does and flipping across the x-axis does. Okay. And so this is the definition for even and odd functions. There are functions that are neither even nor odd, though. And so it would be a function that doesn't reflect across the y-axis back onto itself and doesn't like double reflect to be back onto itself. And that would just like, you know, a simple example would be something like x minus 1 to the power of 2. And so if I flip this, if I make a copy of this and I flip it across the y-axis by making this inside here negative, huh? Where do I need to make it negative? There we go. Okay, yeah, so if I replace this with -x, that's what I'm supposed to do. If I replace this with -x, then you can see it doesn't map back onto itself. And so they don't lie back on top of each other. It's not symmetrical. And if I do both, flipping it across the y-axis and the x-axis, well, now we're even worse. Because now we don't even overlap at a single point. And so this function would be neither even nor odd. And we can show that algebraically as well, where something that would be neither, once again, would be like x minus 1 to the power of 2. If I replace this with f of -x, then we get -x minus 1 all to the power of 2. And if I were to multiply this out, I would get x squared minus, actually plus 2x, and then plus 1. And this can't be factored? Or no, it's x plus 1 squared. And x plus 1 is not in any way equal to, not even just like the negative version of x minus 1 all squared. And so f of x is not equal to f of -x, and f of x is not equal to negative f of -x. And so this one would then be neither even or odd. And so that's kind of what we need to know to be able to talk about the symmetry in the context of this question here. And so what they had asked for us, or the question that they had asked for us, was this. And so they said, for exercises 5 through 8, test for symmetry with respect to each axis and to the origin. And so, I think this would basically just be checking, basically like whether it's even or odd. But we get to, and they tell us to do it with respect to each axis. And so that means we have to not only check if like negative x, like plugging in negative x makes it the same, but also if plugging in negative y makes it the same. Or when they say with respect to each axis and to the origin, I guess when they say like symmetrical with respect to the origin, would that be something that's like rotationally symmetric? Like, you know, x cubed, where like symmetric with respect to the origin would be odd? Okay. And so let's do a couple of these. And so if we do this first one, so we have y equals x squared plus 4x. So this is number 5. We have y equals x squared plus 4x. And so if we plug in negative x, and so if we replace this with negative x, then we would get y equals negative x all squared plus 4 times negative x. And so this would be y is equal to x squared minus 4x. And so in this case, looking at this, this is not symmetrical, not at least with the y-axis. So by negating x, we're flipping across the y-axis, because, you know, it's not symmetrical, and it's not even like the negative version of itself, and so it doesn't appear to have symmetry with respect to the origin either. But let's check if we replace it with negative y. And so if we were to make this negative y is equal to x squared plus 4x, well then in this case we do get y is equal to negative x squared plus 4x. And so I'm trying to think what exactly that would mean in terms of the y-axis. And so, right, well, so now, so like, they told us to check symmetry with respect to each axis. And so, like, you know, plugging in negative x for x and seeing if it's equal to the same thing would be basically checking for symmetry on the y-axis. And then if you plug in negative y for y, then you would be checking symmetry across the x-axis. And so I was just thinking, right. And I was just thinking, it's like, what would like something that's odd, but like put in terms of like the like across the x-axis look like. And so I know this would be like a parabola, and so, but does this somehow show that this could be like symmetrical about the origin? Or a y? Right. I mean, because then if we're saying like y is a function of x, so this would be like f of x is equal to x squared plus 4x. And so then all we've said is that, like, all we've really said here is that if we make this side negative, then f of x is equal to negative f of x. Or no, well, that's not what we're saying. But if we're saying if we make this side negative, we're basically just saying negative f of x is equal to negative f of x, which is not what it means for something to be odd. Yeah. Yeah. I guess we could try that. Just see if it's possible. I don't know, is it, well, we would need like a plus or minus function. We would need to complete the square. And then, I mean, well, we could do it. So this would be y plus 4 is equal to x squared plus 4x plus 4. Or here, I'll write this with minus 4 on this side. Actually, I'm gonna have to add it anyways, so I may as well just add it. Plus 4. And so then this will be x plus 2 all squared is equal to y plus 4. And so this is x plus 2 is equal to plus or minus y plus 4. And so we can say that a function in terms of y, so let's say g of y will be equal to plus or minus y plus 4 minus 2. And so then now if we plugged in negative y into this, then this would be... Oh yeah, I missed the square root. Thank you. Also, we can't hear Pen. Oh my gosh. Pen, can you say something?
Yes, I am. Can you hear me?
Oh my
now, chat?
gosh.
You're looking very dashing today.
This is so upsetting. Anyways. Problem solved. It was all my fault. I had to hit a button to unmute Discord for stream. But so if we replace, so now we have its g of y is equal to plus or minus the square root of y plus 4, all minus 2. And so now if I replace this with minus y, so once again, this would be like checking for symmetry across the x-axis. Then this would be plus or minus the square root of negative y minus 4 minus 2. And I don't see anything really to do with this.
Yeah, it doesn't look very nice to me.
I don't think that there would be any way to like factor out a y in such, or like the negative in such a way that this would end up being like minus or plus the square root of y plus 4 plus 2, I guess is what it would need to become. And so this looks like it is not symmetrical with the x-axis to me, which we knew it wouldn't be. And it looks like it's not rotationally symmetric about the origin either, which we also knew it wouldn't be, because once again this is like the equation of a parabola. Okay, how about another one?
Choose a relation. Like 8 looks kind of fun.
Yeah, I was thinking
7 or 8. Like
7
that has,
or
like,
8.
a little bit more. Yeah.
Let's do 8. And so we have 8 it was x times y was equal to negative 2. And so for this one, it's still the same sort of process where, I don't know, I guess it would probably make the most sense still to kind of write one as a function of the other and then substitute it to kind of put it in terms of seeing it as being even or odd. And so if I write this first as like y is equal to -2 over x, then we can say that y is a function of x such that f of x is equal to -2 over x. And so then f of negative x. And so once again, this would be checking for symmetry across the y-axis. And so this will be -2 over negative x, which will just end up being 2 over x. And so in this case, that is interesting because this would just be f of x negated. And so if we were to make this negative f of negative x, then we would get our original function again. And so that would imply to us that this, at least, about the y, or that would imply to us that this function is odd. Which kind of, as we've talked about, I feel convinced that that means that, it's symmetric about the origin. And so, and to write it out here then, so one way that I could write this is, since we have this negative on the bottom, if I just keep the negative here on top and just factor that negative that's with the x all the way out front, then we can see that f of negative x is just equal to negative f of x, which is what it means for a function to be odd. And so this one seems to be symmetrical. And so I should write up here for number 5 that this one seems to have no symmetry. Symmetry. 2 m's. But this one, at least so far, does seem to be symmetrical about the origin. And so then let's check it for the x-axis. And so if we then write this as a function of y instead, and so we get x is equal to -2 over y, and so then we'll say x is a function called g, that is a function of y, that is -2 over y, then we end up seeing essentially the same thing. So we get g of -y is going to be equal to -2 over -y, which I will write as -2 over y, which is just negative g of y. And so once again, that all that shows is symmetry about the origin. It shows that across the, whether we're looking at it in terms of the x-axis or in terms of the y-axis, the function is odd. And so it doesn't seem like we have any symmetry about the x-axis or y-axis unless you count the origin, which would be kind of symmetry across both. Can we find one that's has it's symmetrical about one but not the other? Or maybe a function that would be odd but have... Well, that's kind of an interesting question to think about. Is it possible for something to have symmetry about the origin and any of the axes? I don't think so. So then that wouldn't work.
Oh, that's fun. So you want it to have odd symmetry, but also even symmetry about one of the axes?
Yeah, but I don't think it's possible.
I think you're right, because then you'd have to have the same kind of shape in each 4 quadrants.
Right. Because if it's true, if you have say half a something parabola looking in quadrant 1 and quadrant 3, then for it to be y equals 0, I don't know that it's...
I guess.
Well, I mean, I feel like y equals 0, you would still say that it has symmetry across the x-axis, though.
It also has that like rotational odd symmetry that you're looking for, yeah.
Yeah. Yeah, I guess that one has both symmetries. And so it has symmetry for x and y and the origin. And so that one has all of them. But I wonder if you can find one that's just two.
Interesting, right? Like as soon as you start to try to draw something in like quadrant 1, for example, right?
Right. If it's
and
odd,
anything.
If it's symmetrical about the origin, then you'd have to draw its like mirror in quadrant 3.
Yeah.
But then if you wanted it to then be symmetrical across like the y-axis, then whatever you draw in quadrant 1 that you also drew its mirror in quadrant 3, you would now have to draw in quadrant 2 and quadrant 4. And that like you get like the symmetry across the x-axis and the y-axis for free, essentially, if you try and do that.
Cool. Oh my gosh. So there's a lot of polar graphs that'll do that.
Like how do you mean?
You were talking about polar coordinates, right?
Yeah.
So aren't there like polar graphs that'll do that?
Yeah, if you I guess if you were to like the flowery type ones, like if you have like
I did r equals cos 4 theta, for example. We could even decrease the number of thetas, like 2 theta or whatever, right?
Yeah, I guess if it's as long as it's a even multiple.
Yeah.
But it's like you could imagine, like if you were trying to graph, like r equals sine of 2 theta. Then if you just started with like, okay, I want to make it odd, then you would like ignore what this would be like up to, or if this is cosine, then does it do what I want? Not exactly. But basically it's like if you were to like start to be like, all right, I'm going to draw this lobe and I want this graph to be odd. And so I'm also going to draw it in quadrant 3, but like flipped over. And then you're like, okay. And so now I've got my odd symmetry, but I also want this to have symmetry across the x-axis. Then you would draw whatever you drew in lobe or in quadrant 1 flipped in quadrant 4, but then you'd also have to draw whatever you drew in quadrant 3 flipped in quadrant 2. And since what you drew in quadrant 3 is already like a mirrored version, or like a mirrored and reflected version, or whatever you want to say, of what you drew in quadrant 1, then basically it's like you can't get like a... Like, you can't make something that's, like, rotationally, like, symmetric about the origin and only one axis.
Yeah, I completely agree.
If it's symmetrical
it's
about...
cool, though, like...
Yeah. And so this is kind of, like, a good, like, snapshot into, like, the things that you, like, think about, I guess, or, like, the questions you might ask yourself whenever you're, like, learning about math. It's like, you're like, okay, well, so, you know... Is it possible for like is it possible for this sort of thing to happen? And it turns out the answer is no. You can't be symmetric about the origin and only one axis. So it seems. Okay, so now for
it looks like it's gonna it looks like it's actually gonna fail to be a function, right? At least in the XY, like with XY coordinates.
Right. Right. It would have to be some sort of relation. If it were rectangular coordinates. Actually, like, that's a totally other thought altogether that I hadn't even considered. Like, even and odd for polar coordinates, would mean like negating theta or negating r.
But Mike, I wonder if it works so easily in polar coordinates because you draw the function so differently, right?
Right.
Like, I almost feel like you'd have to draw it in like a rectangular way to make the definitions work. But I know what you're asking, and I think it would be really, really weird to think about it.
Yeah, because I mean, well, like if you negate r, then you're just like flipping it through the origin to the other side. And if you negate
Right.
theta, then you're just like drawing it going clockwise instead of counterclockwise. But like, what does that really mean in terms of symmetry, I guess, is the question. If you negate theta in a polar function, is that the same as flipping it across the x-axis?
Oh, theta's the rotational element, so it's the equivalent of drawing it backwards.
Right. But if you always start by drawing it at the x-axis and going up, now you're instead going to start at the x-axis and go down.
Right, right.
And so does that just flip it across the x-axis?
Oh, I understand. Yeah, I guess that's a good question, right? Like these are cool questions.
Yes, it is.
Yes.
Yes.
It seems reasonable for like very simplistic sine and cosine kind of functions. Yeah.
Right. But I mean, I might argue that logic holds true always. But I don't have a proof for it. The proof I could not fit the proof within the margins of this page.
Wait, who did that? Who was that?
That was a Fermat.
Fermat, right? This is like the Fermat's last theorem.
Right, right.
That was the very, very subtle joke, but I appreciate it.
I'm glad you picked up on it. Okay, so now we've got using intercepts and symmetry to sketch a graph are our next questions. Let's see, how many questions do we have here? It's a lot. Okay, let's see if we can at least get through this first portion that isn't exactly like all of it, but it's before the problem solving portion. And so let's do like this one here. Let's do number 12. This one will be interesting. And so number 12 says y squared is equal to x minus, or 9 minus x. Sly Robot. Welcome in. Thank you for the follow. And so we have y squared is equal to 9 minus x. And so if we first wanted to find our x-intercepts and our y-intercepts, and then we'll ask about symmetry. Now for periodic functions, are n pi periodic functions odd when n is odd and even when n is even? You got me wondering.
Good. That's the
Are we
point of
talking?
math.
Are we talking about like in terms of polar coordinates? What does it even mean?
Like you're wondering about a function that repeats over n pi, basically, right?
Right. So x-intercept, we set y equal to 0, and so that would be 0 is equal to 9 minus x, and so x equals 9, and so we get an x-intercept at 9 comma 0. For this one, y-intercept, we set x equals 0, And so we get y squared is equal to 9 minus 0. But I will omit the minus 0 for now and forever. And so we get that y would be equal to plus or minus 3. And so it's a good reminder to remember that when I always thought of it as like, you know, whenever you are taking the square root of both sides to eliminate something that's squared, you have to also then compensate for the fact that when we did have y squared equals 9, that whatever the value of y was could have been positive 3 squared, but it also could have been negative 3 squared. And so the kind of my rule of thumb is like, if you're the one taking the square root of both sides to eliminate that power, then you have to make it plus or minus. But so that means we get a y-intercept at 2 spots. We get 2 y-intercepts, one at negative or at 0, negative 3 and 0, 3. If it repeats n times in a circle, can we know its symmetry? And I think the answer is not necessarily in polar coordinates. Yeah, I mean, one thing that I think about is if you have like a polar function like that where it's it's like angle, like its period is like an irrational number or something like that. Where it's like, can you make it so that basically like it never overlaps on itself? Like if you make it like sine of 1 plus the square root of 5 over 2 times theta. And so we get our 2 y-intercepts. And so then now we can ask ourselves about, you know, what symmetries does this have? And so we can see here right away, if we make this x negative, then this will become y squared equals 9 plus x. And so it's not symmetrical across the y-axis. But if we make the y negative, and so it'll be like negative y all squared, then that won't change anything. And so that means that it is symmetrical about the x-axis. Deloitte, are you okay, famished? Are you asking me why,
Famished and
or are you
not
just
okay?
like breaking down? Would you like me to explain this step again? And so like why it's symmetrical across the x-axis? No, you're fine. Oh, so you're just like having a moment? It's okay. It happens to me too. Okay. And so if we were to graph this using this information, and so we know that we have a x-intercept at 9, 0, and a y-intercept at positive 3 and negative 3. And we know that it's symmetrical with the x-axis. And that this, you know, since this is like y squared, this is going to be like a function of a parabola, but just turned on its side. And so we get something that looks something sort of like this. Just squint and pretend it's like a parabola.
It's a very beautiful parabola.
Oh, you're trying to butter me up, aren't you? Let's see. Let's do another one. Let's do 13. And so 13 says y. Oop. 13 is equal, or says y is equal to the square root of 2 times the square root of 4 minus x. And so for this one, just kind of like looking at this, kind of like inspecting it, one thing that I'm already thinking is that if I make the y negative, then we don't get like any sort of symmetry. That will just make the function negative. Or if we make the x negative, then there's no way those like negatives cancel out. And so this one immediately seems not to have any symmetry to me of any kind. And that's what I would expect for something to kind of be like derived from the square root parent function. I wouldn't expect it to have any like x, y, or origin symmetry. And so let's just look for our x-intercepts and our y-intercepts. And so if I set x equal to 0, then we'll get y is equal to 2 times the square root of 4 minus 0, which is just going to be 2 times the square root of 4, which is 2 times 2, which is 4. And so we would get a, what was that? That was setting x equal to 0. So we get a y-intercept at 0, 4. Then for the x-intercept, we set y equal to 0. And so we get 0 is equal to 2 times the square root of 4 minus x. And so if we divide both sides by 2, 0 divided by 2 is still 0. And so then we get the square root of 4 minus x is equal to 0. If I then square both sides, 0 squared is 0. And so we get 4 minus x is equal to 0. And so x is going to be just equal to 4. And so then when x is 4, y is 0. And so then if we were to do a graph, then we would get a point here at 4, 0 and positive 0, 4. And then our graph would kind of, our graph would be going off and to the left like this, because it's the square root function. But since this x on the inside is negative, then it's like flipped across the y-axis compared to the parent function. And so then it would go off kind of in this direction. A full triangle could never be expressed as a function of one variable, though. I mean, you could parameterize it, couldn't you? I feel like maybe you could.
Yeah, you can always parameterize a parabola or a section of a parabola, I'm pretty sure.
Mm-hmm. Oh, I was reading Obi's question in chat. And so he said a full triangle could never be expressed as a function of one variable. And then I was thinking if you could just parameterize that, but I guess it would have to be like piecewise.
Yeah, that would be a piecewise parameterization, I think.
Yeah. Let's see. In questions 15 through 18, it says find the points of intersection of the graphs of the equations. Okay, so this is like solving a system. And so I don't know if this is actually something that I talked about last week. But let's do 15. And so it says 5x plus 3 equals -1. So 5x plus 3, was it 3y? Yeah, 3y equals -1? -1. And then x minus y is equal to -5. And so there's a couple of different strategies that we can use to kind of solve a system like this. But basically one thing to kind of talk about first, and so I'm using the language of solving a system, but they just say find the points of intersection of the graphs of the equations. And so usually that's kind of like solving a system and finding the points where like the graphs intersect often like refers to the same thing. But the idea is basically like you're looking for a set, like you're looking for a point or a set of points that will essentially make both equations true. And so like if I were to pick a point that was in like the top equation that makes it true, but it doesn't make the bottom equation true, then all I'm really saying is like, okay, this point exists in the function for our top line, but not the function for our bottom line. And so it's like one is a point on the graph, like on a point on the curve, but the other isn't. And so if we try and solve both of them simultaneously, where basically like we find the value that makes both of them true, then what we're saying is that this single point that we found that makes both of them true, like appears on both lines at the same time, and therefore must be an intersection. And so one way that we can kind of like do that we can kind of like restrict it to like find a value that's true for both equations, is like substituting like one variable of one equation into the other equation. So like for instance, if we took this bottom equation here and add y to both sides, then we can say that x is equal to y plus 5, or it's minus 5. And so if x is equal to y minus 5, well then, if that's something that has to be true for our bottom equation, well then it needs to be true for our top equation as well, for it to make it true for both equations. And so I'm going to substitute y, or that x equals y minus 5 into our top equation. And so we'll have 5 times y minus 5 plus 3y is equal to -1. And so then I distribute the 5 through, I get 5y minus 25 plus 3y is equal to -1. And so we get 8y is equal to, if I add 24 to both, or 25 to both sides, then I get 8y is equal to 24. And so then dividing both sides by 8, I get y equals 3. And then I can plug that value of y equals 3 back into this equation right up here. And then I get that x must be 3 minus 5, and so x must be -2. And so the values that make both equations true is when x is equal to -2 and y is equal to 3. And so that means that the point -2, 3 is a point where these two curves intersect. And so let's do another one. And so let's do number 16. And so 16 says we have 2x plus 4y equals 9. Or actually, I mean, okay, I'll do 16, but then I'm also going to do like 18. And so 2x plus 4y equals 9. And then 6x minus 4y is equal to 7. And so there is another strategy that we can kind of do here. It's called the one that we just did on this previous question was called like the substitution method, where we solved one equation and then we substituted it into the other. This one we're going to do what's called the elimination method. And the idea for the elimination method is that if you add like the equations together, like you would want to use the elimination method when you could add the equations together, so that one of the variables cancels out. And so like the reason that you can do that is because it would be like the same thing. Like if we say that 6x minus 4y is equal to 7, well, it would be the same thing as looking at the top equation and adding 7 to both sides. Except on one side, instead of adding 7, you're adding 6x minus 4y, which is equal to 7. So it works. It doesn't like break any, like it doesn't break the property of equality, like the addition property of equality or anything. Which is, you know, that's kind of like in math, I feel like one of the best sort of things to think through and the best sort of things to keep in the back of your mind. You know, a lot of the problems that people have with like algebra and things like that is not understanding like when like things are kind of like obeying the laws of algebra and when they are not. And so it's like, what do you mean you can just add two equations together? Well, and it's like, well, really, it's like we can we can create a third equation that would be equivalent to as if we had added both equations together. It's kind of maybe like a better way to think about it. But all that aside, if we do 2x plus 6x, we'd get 8x. And then 4y minus 4y, we'd get 0y. And then this will be equal to 16. And so then we get 8x is equal to 16. And so x is equal to 2. And then we can plug x equals 2 back up into one of these equations. I'll plug it into the first one. And so this will be 2 times 2 plus 4 times y is equal to 9. And so we get 4 plus 4y equals 9. And so 4y equals 5. And so y equals 4/5, or 5/4. And so the point of intersection for these two curves would be at 2, 5/4. And so let's do 18 now. 18 looks interesting. And so 18 says we have x squared plus y squared equals 1. And negative x plus y equals 1 as well. And so, so we want to find values for x and y, which means we want to like get rid of one of the variables. And so probably the most sensible way to do that here would again be like by substitution, because there's no way we could add these equations together without doing something funky first. Actually, there is something funky we could do. Okay, I'm going to show this two ways. And so if we add x to both sides, then I get y is equal to x plus 1. And then I can substitute y equals x plus 1 up into this first equation. And so we get x squared plus x plus 1 all squared is equal to 1. And then if I FOIL this out, we get x squared plus 2x plus 1 is equal to 1. And so we get, if I subtract 1 from both sides, then I get 2x squared plus 2x is equal to 0. And so I can divide both sides by 2, factor out an x, and so we get x times x plus 1 is equal to 0. And so that means x must be equal to 0 and negative 1. And now if we plug both of these values for x back into either of these equations, we could figure out what our values for y need to be. And so if I plug it into just this equation right here, then I get y has to be equal to, when x is 0, y has to be 1. And when x is negative 1, y has to be 0. And it's important to put it that way because, once again, you have to think, we're thinking about points here. And so when x is 0, y has to be 1. And when x is negative 1, y has to be 0. And so this would be like our solution set here. And so the thing that I spotted, though, when I was looking at this a moment ago, is if I take this bottom equation and I square both sides. So if I copy this here, I have somehow bugged out my OneNote. Oh, there we go, it's back. If I were to square both sides of this bottom equation, well, 1 squared is still just 1, but negative x plus y squared is going to be a difference of squares. Is that? No, it's not. Whoops. Well, the x squared will still cancel out, but then we'll have the xy term. Okay, never mind. As soon as I went to write it out and think through it in my head, I changed my mind. Let's see, what is this pen?
So I went down a rabbit hole.
Polar
trying to
equations
figure
for
out
symmetry.
Yeah, I went down a rabbit hole, and then they had like some tests you could do for symmetry in polar coordinates, and they turned out to be like really interesting. So I posted them in the Argonauts for people to reference.
Squaring still works? Yeah, well, it's just, I was thinking if you squared this, you'll get x squared plus y squared. But then you'll also get like the minus 2xy. And you could subtract those equations from each other, but then you would get like a 2xy. And so I was thinking if it was like a difference of squares somehow, then like either the x squared or the y squared would cancel out. But it wouldn't, like, squaring it and then like adding the equations wouldn't have simplified anything out, Zone Ranger. Two xy equals 0, so x equals 0 or y equals 0. Oh, yeah. And then you plug both of those back in. Okay, that would have worked. That would have been interesting. Wish I thought of it. But yeah, this is interesting, Pen. You know, kind of like going from the idea of like symmetry with like even and odd and that sort of stuff. For like rectangular coordinates, I guess it would make sense that it's true, like that there's something similar for polar coordinates as well.
Yeah, so they're like, I like that they talk about the kind of like r versus negative r symmetry, the theta versus negative theta symmetry, but there's also the one that we're kind of really curious about, which is the rotation by 180 degrees, which I think is the pi minus theta rotation that they're talking about, but I'd have to read it a bit more to see exactly what it is. But
yeah, that would do it. I would think it would be pi.
It feels like it's the pi minus 1/8, like the pi
right.
minus
pi minus theta
symmetry that they're looking at. Yeah.
Because that would mean that you've like advanced it by pi rotation, and then you're gonna draw it backwards from there, or whatever. Yeah, interesting. And so I guess Penn posted that in my server. If anyone else wants to go look through that. In exercise 19 and 20, plot the points and find the slope of the line passing through them. And so if you've taken algebra, or if you were here last week, you might remember that we can say like the slope through 2 points, basically like how far up, like one way you can, the way that we often describe the slope is it's basically like the change in y over the change in x. Maybe you've heard like the mnemonic before of like rise over run. Which basically it's like how far you go up and how far you have to go over to like get to the next point on the line, or at least a multiple of it. And so when they tell us to kind of find the slope between these 2 points, so they gave us, let's do 20, because 20 just, never mind, I'll do 19. And so they gave us 3 over 2 comma 1 and 5 comma 5 over 2. So 3 over 2 comma 1 and 5 comma 5 over 2. And so so basically it's just like, what is the change in the y values? And so it could be 5 over 2 minus 1. And so that would be like, what's the change from, this point up to this point? And then it'll also on bottom, it'll be 5 minus 3 over 2. Sometimes this formula for slope is written as like y1 minus y2 over x1 minus x2. Or you'll even sometimes see it written where it's like y2 minus y1 or x2 minus x1. But there really is no like, you don't like, one of these doesn't have to be 0.1 and the other has to be 0.2, or like vice versa. Like either of them can be 0.1 and then the other one would just be 0.2. And the math will work out exactly the same. In theory though, it is, I guess, easier that if like one point has both of its values being larger, then that would be like the first point, like your 0.1 that you'd want to pick. You would do its values minus the other one's values. Just one thing to kind of be careful of, though, is that like you just can't like mix and match them. Like if you do 5 minus 1, you can't then do 3 over 2 minus 5 on bottom, because that would be like mixing up which one you're getting from like 0.1 and which one you're getting from 0.2. But at any rate, 5 over 2 minus 1 is going to be 3 over 2. And then 5 minus 3 over 2 is going to be 7 over 2. And so 3 over 2 over 7 over 2 is just going to be 3 over 7. And so that's our slope between those 2 points. That's number 19. So for number 20, okay, so for number 20, the points they gave us are -7, 8 and -1, 8. And so we could go through and plug this into the formula, but what I encourage you more so to notice is that the y values are the same. And so we see that it's -7, 8 and -1, 8. And so the y value doesn't change at all. And so we don't go up or down. And so our change in y on top will just be 0. And so it doesn't matter what our change in x is, our slope is still just 0. And so that's like a point where it's like, if you're just the type of person who just only uses algorithms and you just only plug things in and you don't do anything else, then like you would miss that and it would be just more work. And so it's always better to understand, I guess is the point there. Find an equation of the line that passes through the point and has the indicated slope. Then sketch the line. And so for this, here's where it's like useful to like know all the different types of like ways you can write like a linear equation. And so point slope form is one of my favorites. And so point slope form is y minus y1.
I hope your math continues to be fun as fucking fuck. I really have to go to sleep.
Whoa.
I hope you all have a lovely night because you deserve it, dog. I smooch y'all.
I'm sure this math is going to be so fun. Good night, fool. I hope you have a good evening. And so point slope form is y minus y1 is equal to m times x minus x1, where m is our slope, and then x1 and y1 are just like, is like a point that we know is on the line. And so for this question, that makes things relatively simple for us. And so if we know that like one of our points is 3 comma negative 5 and our slope is 7/4, then that would just be like saying that like our x1 comma y1 is equal to 3 and negative 5, and that our slope is 7/4. And so we just plug those in. And so that will be y plus 5 is equal to 7/4 times x minus 3. And the other questions are going to be pretty similar. One thing to kind of keep in mind is with like when the slope is unidentified, slope is undefined, that usually means that it's like a vertical line. And so that would be like you have at negative 8 comma 1, it's going through like a vertical line. Or like the line going through that point is just vertical, straight up and down. If the slope is 0, that just means it's horizontal. In exercises 25 through 28, use slope and y-intercept to sketch a graph of the equation. And so, once again, this is kind of like, it's good to know what the other forms of like, that you can see that these straight lines come in. And so like 27, if we look at 27 just really quick. And so 27 is y is equal to 4x minus 2. And so this resembles y equals mx plus b form. Oh, wow, you're still going? It's only been 3.5 hours. I am literally a machine. Literally, not literally. And so this resembles like y equals mx plus b form. And so in this particular form, then m is our slope. And so this would be like saying we have a slope of 4, and b is our y-intercept. And so what were they asking us to do? They want us to graph the equation. And so this is our x-axis and our y-axis. And so it's -2, and I only gave me the first quadrant. And so then we would start down here at -2. And then we have a slope of 4. And so you can interpret 4 as being like 4/1. And so as a reminder, like slope is like change in y over change in x. It's like our rise over run. And so if we have a slope of 4/1, then that means if we were to go up 4 points and then over 1 point, then that should also be a point on our graph. And so that would be maybe about here. And then we could go up 4 and over 4 again, and then up 4 and over 4 again. And then we would get this line. There we go. Close enough. And so on questions like 25 and 26, where it's just y equals 6 and x equals -3, one way that I like to explain this that, you know, I feel like makes it make sense for me in a way that like it didn't make sense whenever I initially learned it in school, is when you have something like y equals 6, what can x be equal to? If I want to ask a question, should I put it on chat, on Discord, or have you already realized I'm going to end up trolling you? You can put it wherever your heart desires, Jeff. I am prepared to be trolled. And so whenever you have something like y equals 6, I think it's good to ask, like, what can x be equal to? And then you might be like, well, I don't see an x, so how am I supposed to know? But one way that you can think about this is, if there isn't an x, then you could potentially like make an x. And so if I were to multiply both sides of this by x, then this would be like xy is equal to 6x. And now in this case, it doesn't matter what x is, because like anything that you plug in for x, it's just going to, make both sides, like it's still like not going to break anything on either side. And so x can be like any value. And so even though our original equation, y equals 6, doesn't contain an x, this is just essentially to like kind of show that x can be anything.
Prevent Jeff from making us dive into a mathematical rabbit hole?
But y is restricted to be exactly at 6. And so if x can be anything but y has to be 6, then that means it's a horizontal line
the infamous
with a height of
Jeff,
6.
master of mathematical mischief. Well, to thwart his wily ways, distract him with a well-placed butt joke, or perhaps summon 7 to block his path with some shiny scales. Otherwise, you'll find yourself lost in a never-ending equation maze. Yep.
He knows you so well. Just distract him with butt jokes. And so then this would be at 0,6. But why? Ha! And so x can be literally anything. And so if x can be any value but y must always be 6, then that's why we end up with like a horizontal line. And in the case of like x equals -3, then it's the same case. Y can be anything. We're not restricting y's value at all, but x must be -3. And so that would be like a vertical line at -3 on the x-axis. Do I go beep boop? Am I a Bobot? No. Am cyborg. You might not like it, but this is what peak performance looks like. In exercise 29 and 30, find the equation of a line that passes through the points, then sketch the line. And so this is kind of like a continuation of when we did like 21, except we just have to calculate the slope too now. And so for number 29, it's actually, I don't like, I could look at this pair of points here and see, to go from 0, 0 to 8, 2, we'd have to go up 2 and over 8. And so I will just go directly to that for my slope. And so my slope is 2 over 8, which will be 1 over 4. The way I check is an EMP. If it dies, then Bobot. I've been thinking about doing GIS stuff in JS directly on the user's computer. Do you know of any good 3D KD tree libraries for JS? Is JS JavaScript? GIS stuff?
And and more importantly, does KD stand for craft dinner?
Yeah. And what's GIS? Like, am I creative enough
GIS
to come
is
up?
usually like it's usually like geographic interface, like geographical information services. Yeah, it's like data science with maps.
Oh. Who was it that came? Once upon a time, someone came into my chat and they're asking me about like slippy tiles or something like that, which is like the the tiles that you would get from, like, if you were to... That was Jeff? I still think about that from time to time. I haven't sat down and done anything else about it. But it's like the tiles that you get if you were to, like, cut the, like, globe up into tiles along latitude and longitude lines, where they're, like, more square near the equator, but they become more triangular near the poles.
Those are called slippy tiles?
Yeah. Once upon a time, you streamed Islands of Insight. I'm still planning to stream more of that at some point, though I never exported my online data, so I'll have to start over. OpenStreetMap calls them slippy tiles, apparently.
Wait. OpenStreetMap? Like, that seems like it's a very localized thing, when slippy tiles are literally feel like a more global thing.
It sounds like maybe Jeff can explain. Okay, find the equation of a line that passes through the points. And so another point that we have is 0, 0. And so we can just use point slope form. And so this will be y minus 0 is equal to 1/4 times x minus 0, which will be y is equal to 1/4 x. Or another thing that you can kind of do is, you know, at least for this specific question, since they gave us the point where the x value is 0, then we know that the y-intercept is 0. And so we could even just use slope-intercept form, which is y equals mx plus b, just taking b to be 0. And so it'll just be y equals mx, which is what we get anyways. And so there's a couple of ways to kind of, like, work to the answer conceptually. Slippy tiles at zoom level 0 cover most of the globe. Slippy tiles zoom level 0 won't cover latitudes above 85 or below 85. Negative 85. Huh. I was spending some time thinking about, like, the other day, like, at the pole, are the slippy tiles technically triangles? At least in the sense that, like, one that intersects the pole would only have 3 vertices.
Like, I feel like up there it would get...
the tiles
it
are
would get super
infinitely
infinite
tall.
up there.
Oh. Oh, because I guess when we're talking about the tiles, we're not talking about what they actually look like on... Like, what they would look like on the globe. We're talking about what they would look like projected onto a square. I see. This math game
so
looks fun. Does it have a skill tree? It does! And so I'm helping everyone in chat grinding experience right now for their algebra math skill. You should join in.
Oh my gosh, I feel like we should create a skill tree for calculus. That would be so fun.
My experience bar broke. Where do you want to put your skill points into trig substitutions, or do you want to put your skill points into, you know, taking care of your physical well-being? Because you have to you can only pick one. you have to either study or not. Just kidding. When I say I don't want to interrupt, I'm lying. Gudermanian function. Is this like part of, like, your research or something, Jeff? Or, like, are you just doing this for fun or because you're interested? Unfortunately, at a certain point, I became so stressed about school where it becomes something almost impossible to do things labeled homework for fun. It's tough. it's tough. It's like you have to step away from it long enough and think about it long enough to realize that maybe it's actually something that you want to do, even though it is hard or academic, given that you had prior difficult experiences in the past with academics. And you don't necessarily have to go back and be an academic anyways.
And I wonder if, like, one thing too, like, I know, like, colleges and universities typically stress that you have to do things by yourself, but I always find math, like, very accessible when you do it with other people.
Mm-hmm.
Right? Like, you get a chance to talk to other people about how you're thinking about stuff and how they're thinking about stuff, and you get to make a lot more sense that way. So, I don't know, like, just do math with other people. That's like my takeaway.
Whenever I go back to school in the summer, which is currently my plan, I plan on streaming a lot of homework. That's my plan. And so then you can learn the same thing that I'm learning along with me. Find equations of the lines passing through -3, 5 and having the following characteristics. Okay, so they're telling us we're going to keep this point. It's always going to go through -3, 5. What are you going to learn? So I'm going back for math. I have like 78% of my required credits, but most of that was from doing engineering. And so even though I've learned a fair bit of linear algebra, all like just on my own, I need to go actually take linear algebra. I need to take abstract algebra, and probably some like other like lower division math courses too, like history of math or something like that. And so there's going to be lots of fun stuff on the horizons here.
I'm actually super excited for you. Like, history of math was one of my favorite classes to take.
I don't know. I mean, but there's no math in it.
It's you kind of say that, but there's a lot more interesting math than you think that there will be in a course like that.
Okay, interesting. Yeah, I guess I don't know. I'm looking forward to all of it. I don't know. I'm gonna have to figure out how to reconcile just how much of like a not morning person I've like come to be in the past year or whatever. When are you going to purchase the Bad Math Jokes 2 upgrade? I mean,
the world wants to know.
I mean, how many upgrades are there? Does it go up to like Bad Math Jokes 40? Okay, so we have a point, -3, 5. And so in part A, they say write an equation where it has a slope of 7/16. And so m would be 7/16. And so again, we can just use point slope form, where we have y minus 5 is equal to 7/16 times m plus 3. Or what? M? X plus 3. I'll get V2 for free this summer.
Yeah, going back and taking abstract algebra and history of math, like, I think you're going to get a free upgrade for sure.
So as you know, a verified math historian, what is your opinion on Newton? Quote unquote.
My opinion on
yeah,
Newton?
quote
Oh,
unquote,
wow.
quote unquote inventor of calculus.
Well, quote unquote inventor of calculus is false. because-
Exactly.
Yeah, when you take history of math, you understand that it was It was a duality, right? Like, I think
Right.
that Newton and Leibniz were doing things roughly at the same time, and it was the Royal Mathematical Society of the UK that decided that Newton, quote unquote, was the originator, which is why Leibniz ended up having a terrible passing.
Right, but it was also like a lot of the people on the committee were like Newton's friends.
Yeah, exactly. Like the cards were stacked in Newton's favor. Absolutely, I agree.
Right, and he took advantage of it. Who was it?
Yeah,
Someone.
no.
I think it was like someone came into my chat and I was like talking bad on Newton, and they were like, "How dare you?"
I mean, they were probably from the Royal Mathematical Society of the UK.
Okay,
Right, like
so
they got to save face. They got to be like, "Yo, we made this decision, a couple hundred years ago. We got to save face on this still."
So for part B here, they want us to write an equation that's parallel to this one. And so this is good. So if we rearrange this equation just so that we can kind of see its slope more clearly, if I subtract 5x from both sides and then divide both sides by -3, we'll get y is equal to 5 over 3x and then -1. And so this line has a slope of 5 over 3. And so we want to write the equation of a line that's parallel to this one. And so if it's parallel, then that means that they have to have the same slope. Basically the same change in y over the same change in x.
Because some people call me an LL, a Leibniz lover.
Hell yeah. But that basically just means we need it to go through this point and to have a slope of 5 over 3. And so this would just be y minus 5 is equal to 5/3 x plus 3. And so point slope form, still going through the same point. Only thing that's different is the slope. And so the next one would be perpendicular to 3x plus 4y equals 8. And so 3x plus 4y is equal to 8. And so if we want perpendicular to this one, well, we still want to know the slope. And so if we subtract 3x and divide by 4, we'll get y is equal to -3 over 4x plus 2. Newton did some good stuff, was just a bad sharer of the spotlight. Newton was like a sore winner. It's just like
That's a good way to describe it, actually.
it's just like, come on, dude. So if we want a line that's perpendicular to this one, so one thing that you might think of to like make it perpendicular is just to like switch the change in y and the change in x. But if you think of doing that for like a really steep line, something like maybe like 1 over 10, if we just made it like 10 over 1, then it's now still really steep, just in the other like direction. And so we need to kind of do... I think you're an abysmal winner. What is that from, Yeet? And so we have to flip it, like basically we have to flip it over, but also make it negative. And so just using my, trusty point slope form again, it'll be y minus 5 is equal to 4/3 times x plus 3. And so by going from a slope of -3 over 4 to a slope of 4 over 3, then we get that. Now it'll be a slope that is perpendicular to the original line. And then parallel to the y-axis. So if it's parallel to the y-axis, that means its slope is undefined, but it's a vertical line. And so we know how to write vertical lines. It's just like x equals something. And so for part D, it will be x equals, and it will go through the x coordinate of the point we're given. So x equals -3. And so 32 is pretty much the same question, just with different lines and points and stuff. 33. The purchase price of a new machine is $12,500 and its value will decrease by 850 every year. Use this information to write a linear equation that gives the value of t of the machine the value of the machine t years after it is purchased, and then find its value at the end of 3 years. And so, one way we can think about this. So we have some function v, and so I'll call this v of t, and so it starts at 12,500, and then every time. Thanks for having me for a bit, Talus. Absolutely. I hope you enjoy your dinner. And every year, every time t goes up by 1, the total value will decrease by 850. And so this will be minus 850 times t. So after 1 year, it'll go down 850. After 2 years, it'll go down 2 times 850. I asked my dad if he wanted to say anything to y'all, and he said, peace. Thanks, Epic's dad. That means so much to me. Or peace. I can't be sure. Hey, you want a piece of me? Can I have a piece? And then they want us to find what its value will be after 3 years. And so now we just need to find out what v of 3 is. And so this would be 12,500 minus 850 times 3. And what will that be? 24 plus 150. And so this will be 12,500 minus 2550, which will be 9,050, or 9,950. A contractor purchases a piece of equipment for $36,500 and costs an average of $9.25 per hour for fuel and maintenance. The equipment operator is paid $13.50 an hour, and customers are charged $30 per hour. And so, okay, this is a fun question. And so write an equation for the cost, C, of operating this equipment for T hours. And so we have C of T. And so we purchased the equipment. So we purchased the machine for 36,500. So C of T is going to be equal to 36,500. And then it also costs $9.25 per hour for fuel and maintenance. And so that's going to be plus $9.25 times T. And so even though this is like, it's costing $9.25, it's going to be plus, because we're talking about the cost here. And so it cost 36,500, and it's going to cost us an additional $9.25 for each hour we use it. The equipment operator is paid $13.50 per hour. And so that's going to be plus another $13.50 times T, because that's going to be part of our cost as well. And then the customer is charged $30 per hour. And so our revenue, R of T, will just be that 30 times T. And then they say, find the break-even point for this equipment by finding the time at which R is equal to C. Hey Jack, it's going good. How are you? We're just going through the preface section, the review questions of this book. And we're going to be kind of getting started on some more of the deeper calculus stuff next Sunday. And so it says find the break-even point for this equipment by finding a time at which R is equal to C. And so we're just going to set this equal to this. And so 36,500 plus, and then 13 plus 9, is 22. And so 2275 times t is equal to 30t. If only I was taking math. Well, you don't have to take math to tune in to the streams on Sundays or watch the VODs and still learn something. He also wanted me to tell you all about the real Apple Newtons he owns. What's an Apple Newtons? Was it the apple that fell on Newton's head or whatever? That's the first thing I think of. It's complicated. So if I subtract 22.75t from both sides, then we'll be left with 36,500 is equal to 7.25t. And so how many times does 7.25 go into that? It's like an iPad predecessor, but from 1993. That's kind of badass. And so then t would be equal to 5,000 34.48. Is that right? Oh, this is... Wait, yeah, no. 30 minus 22.75, 7.25. Okay, yeah. And then I divide both sides by that. Why is this like a decimal number? Well, maybe it's because 7 doesn't go in very well into whatever this is. 4/8. So it would take like over 5,000 hours. I don't even know how I passed trigger stats. Well, if you have any questions, whenever they come along, you're always welcome to ask. I am happy to help. $5,000 hours is how many hours I play the video games I play for 5,000 hours. Yeah, that's like 5,000 hours. That's like over half of a year. But I guess it's just like, you know, you purchase the machine and you use it for over half of a year. Then you break even. And then however long you continue to use it after like that, I guess Jeff says roughly have 7 months. Then you would get to make that, then it would be profit. In exercises 35 through 38, evaluate the function at the given values of the independent variable. Simplify the result. Okay, so they just want us to take this function, find f of 0, f of 5, f of negative 3, and f of t plus 1. I go with the idea that of $1 equals 1 hour for games and consoles. Well, if you do that, you're going to be missing out on like a lot of good games. And so sometimes there is such a thing as quality over quantity. Like there's lots of games that I've played recently that maybe weren't necessarily very long, and like I paid more than $1 per hour for them. But they were still really good games. LOK Digital was fun. I just played that. What's LOK? Oh, man. Okay. You know, we are just pushing the peak of 4 hours here. Let's finish this page. And then we'll have to finish up the preface next week, I think. And then we'll start into limits and everything like that. All the good stuff. Lock. Digital adaptation of a word puzzle book. Oh. That could be interesting. Okay. Last few questions. So 35 is equal to, the question 35, so we have f of x is equal to 5x plus 4. And they want us to find, it was f of 0, f of 5, f of negative 3, and f of t plus 1, or something like that. Was it plus? It was plus. T plus 1. And so if we plug this, basically like we're trying to figure out what is this function equal to when we say our input is equal to 0. And so x kind of like represents our input variable. And so it's just like we're taking 0 and substituting it into everywhere that we see an x in our function. And so we would end up with 5 times 0 plus 4, which would just be 4. This would be 5 times 5 plus 4 is 29. 5 times negative 3 plus 4 is negative 11. Merry Christmas. What? Are you gifting me things? I was playing more Demon Crawl just like yesterday. This will be 5 of t plus 1 plus 4. And so here, even though this isn't a number, it still works the same way. We're replacing x with t plus 1. And so this is 5 times t plus 1 plus 4. And so we'll distribute that through, and that'll be 5t plus 5 plus 4, which will be 9. I haven't gotten anything on Steam yet. Oh. Or no. I'm sure it will come through in a minute. Okay. And then let's do number 37. And so on 37, so this one's actually really important. So this is like a really important thing that they have here that they're kind of telling us to look at, called the difference quotient. And so first of all, we have 4x, or f of x is equal to 4x cubed. Okay, x squared, thank goodness. And they want us to figure out what is f of x plus delta x. Then minus f of x. And then all over delta x. And so I'm going to explain the difference quotient probably a lot more next week. And really kind of go deep in detail on that. But basically, this just ends up being the slope. And so that's kind of like one simple way you can think about this. Where it's like, we have the function evaluated at some value, and then we go over a little bit. We go over some change in x. And then we find the function at that value. And so if we subtract those, then that's just basically like our change in y. And so then this top is effectively like our change in our function over our change in x. So it's a slope. But if we plug that into the function, then we're replacing x with x plus delta x. So this will be 4 times x plus delta x, all squared, minus 4x squared, all over delta x. And so if we expand this out right here and simplify it, it'll be a little bit weird to write it this way. But this will end up being 4 times x squared plus 2 times x times delta x plus delta x squared. And then minus 4x squared. All over delta x. And so then if I distribute this through, then this will be 4x squared plus 8x times delta x plus 4 times delta x all squared minus 4x squared all over delta x. And then one part of the magic of the difference quotient now is this 4x squared here and this 4x squared here cancel each other out. Then we can cancel out a delta x from everything that's left. I did actually see you open Demon Crawl yesterday. It was shocking to say the least. It's a good game to play when I'm not streaming. I like it. I've been playing with the spy talent. Having like the gleaned information from random cells is super nice. So this will be 8x plus 4 times delta x. And that's what that one's equal to. And then we'll kind of figure out more to do with the difference quotient next week. I feel like unlocking the masteries in Demon Crawl is super tedious. Actually, just unlocking like anything in Demon Crawl is like super tedious. That is like my one critique of the game. And so for the last couple of questions on this page, and so they say find the domain and range of the function. And so one way to think about the domain and range is like the domain is all of the values that you can plug in. Like everything that like you can pick a spot on the x-axis and that value of x can go into the function. There are some values that can't go into the function. And so like if we look at 40, for instance, and so number 40 is g of x is equal to the square root of 6 minus x. Demon Crawl's progression system is terrible. A problem with this is it's designed for you to go infinite to farm stuff. So in normal play, it's unfun. Yeah. It just seems like a lot of the like things to actually unlock. It's just like you have to get so absurdly lucky to like stumble upon a build that can like enable the unlock requirements. But it's just kind of silly sometimes. So for this function, we kind of talked about it a little bit earlier, that it doesn't really make sense to talk about like what's the square root of a negative number, unless you're talking about complex numbers. But in this particular instance, you know, you can kind of assume, like, unless complex numbers are explicitly stated to be on the table, they're usually off the table. But in this case, I would assume that complex numbers are not on the table when talking about like the domain of a function. And so the value of x's that we can plug into this are restricted by making sure that we can't take the square root of a negative number. And so if x in this case, if x were equal to 6, so like if x is equal to 6, then what happens? Well, we would get the square root of 6 minus 6, which is the square root of 0, which is equal to 0. And so there's no problems with that one, but if x is anything larger than 6, so if, for instance, x was equal to 7, then we would have the square root of 6 minus 7, which would be the square root of -1, and now we would start taking like the square root of negative numbers, which doesn't work. And so in this case, we would say the domain for this function would be defined by all the values of x that is less than or equal to 6. Because it can be anything smaller than 6, and x can even be itself be negative, as long as the inside of the square root, the thing that we're taking the square root of, doesn't end up being negative. And then for the range, and so for finding the range, it's helpful once again to kind of know what the parent functions are. And so I know that like the square root of a function looks something like this, kind of going off like a turned over parabola. But this particular one is like, it doesn't have any funny business where it's not like flipped over negative or anything like that, or it's not shifted up or down. And so the range, as in like all of the output values that are possible to kind of like pull out from the graph, is going to be everything greater than 0. And so the range will be y is greater than or equal to 0. Including 0. Let's do 42 really quick, and then we'll call it a night. And so 42, and so this is kind of like another kind of classic case of like, watch out for illegal math operations. Make sure that you're not doing anything illegal out there with your math. And so like one of the things that like I always, like internalized when it came to math is that like you can't divide by 0. And that much is true. And so like taking square roots of negative numbers, that was actually a lie. You can. They're just called complex numbers, and you're just going to have to be careful about them. But like you actually can't divide by 0. At least not within the real numbers or the complex numbers. Maybe there's a number set where it does make sense to divide by 0, but I haven't heard of it. And so here, one of the immediate things to kind of be aware of is like you cannot divide by 0. And so we need to make sure that like x never is equal to a value that would cause us to divide by 0. And so if we take this denominator and set it equal to 0, so x plus 1 is equal to 0, then we get that if we set this denominator equal to 0, then it will be equal to 0 when x is equal to -1. And so therefore, for our domain, it's all real numbers except x is not equal to 1. Add a new set of complex numbers where it equals a number divided by 0. Yes. Yeah, -1. Yeah, but if you do that, H, then like you just immediately start to run into problems where like 2 ampersand you could show is equal to 3 ampersand, which is equal to 4 ampersand. And it's just like all ampersand numbers would be equal to themselves. I have actually thought about this before. And then the range for this particular function. So since this is a rational function, you have to be aware that it could also have like a horizontal asymptote. And so in this case, the horizontal asymptote will appear like it, since the degree of the bottom is higher than the degree of the top, then the horizontal asymptote will be at x is equal to 0. And one way that you can think about this is like, can the function ever be equal to 0? And so like if we take this and we say, okay, 2 over x plus 1, let's set this equal to 0. Is there ever a value that you can pick for x that will make this equal to 0. I mean, if you pick 1, then that'll be 2 divided by 2, but that's just 1, and 1's not equal to 0. And so there actually isn't. And so, you know, this isn't how you would go about finding the horizontal asymptote, because if the horizontal asymptote was just at a different value instead of 0, then you would be able to find a value of x that would make this equal to 0. But in this particular case, you can just think of this as evidence that there is a horizontal asymptote at 0. And so the value like y equals 0 will be excluded from the range. So it'll be all real numbers, but y does not equal to 0, or y is not equal to 0. And we did it! Well, we didn't do it, but we did most of it. And so we have a few questions left, and so I'll probably still cover a few of these, because a few of these are probably pretty interesting at the beginning of next week. And some of these problem-solving ones look really interesting. Like this number 1 here, where it's like finding tangent lines. I think we'll go through that one too. And so we'll finish off the last bit of some of the preface questions next week. And then we will jump into chapter 1 proper. Limits and their properties. Who was that? Can I get his number? That's Oliver Heaviside. He created the Heaviside function. Look him up. Grab a phone book. Okay. He liked steps. It's true. He made the step function. Oh, he's dead. Yeah, 1925. Double check Steam. Maybe it hasn't sent it to me yet because I still have things running. What happens if no one does? Then you'll just keep it, I think. Or maybe it'll take it from you and give it to no one. I don't know. Thank you for the head pats. Thank you, bees. Thank you for the math. Thank you for being here and joining me. I hope you learned something, or even if you didn't learn anything, I hope this was, you know, wonderful background noise. You know, I'm sure for a lot of people here, this math is kind of like below where you're at, or maybe above where you're at. But even if you're even if you're far ahead of where this type of math is, I hope that I can like provide some sort of insight, and kind of like help understand some things more deeply. Yeah, you might even consider this stream to be a little island of insight of mathematics. One could say that. What about ice height? Huh? Alright, good night everybody. Hope you all have a wonderful evening.